What lies beyond the event horizon of a black hole? Are we alone in the universe, or are there civilizations more advanced than we can imagine? Join us as we delve into strange objects, bizarre planets, enigmatic galaxies, and groundbreaking theories that push the limits of science and our knowledge. Imagine a cosmic mirror to black holes, these voracious entities from which nothing can escape, not even light. Enter the white hole, a theoretical marvel proposed by the same equations that describe black holes. Unlike a black hole that draws everything into its inescapable grip, a white hole would repel all matter and energy, expelling them with such force that nothing could penetrate its bounds. This concept, while still speculative, is a tantalizing enigma within the fabric of our universe. If such an entity were ever discovered, it could revolutionize our understanding of space-time and gravitational phenomena. The implications of finding a white hole would ripple through the fabric of cosmological theories. It would provide a concrete example of time symmetry in general relativity. Imagine tracing the life of a black hole backward. You would theoretically encounter a white hole. Such a discovery could lead to a better understanding of information paradoxes concerning black holes. For instance, while black holes trap information possibly forever, white holes might expel it, offering clues into how data might be preserved in the universe. Furthermore, the study of white holes could unlock new insights into the nature of singularities and the origins of our cosmos, considering that some cosmologists even speculate that the Big Bang itself might resemble a white hole explosion, scattering matter uniformly throughout the nascent universe. This transformative concept challenges our view of creation and entropy on the grandest scale possible. Wormholes, often referred to as Einstein-Rosen bridges, are hypothetical passageways through space-time that could connect distant points within the cosmos far more quickly than traditional travel would allow. Picture space as a two-dimensional sheet of paper, and a wormhole as a tunnel thrown through folded layers of that paper, providing a shortcut from one side to the other. These intriguing constructs arise from solutions to the equations of general relativity, implicating massive gravitational fields, bending and warping space-time to create such connections. Traveling through a wormhole, if one were ever found and made stable enough for passage, would be an unimaginable adventure. As you approach the entrance, a swirling vortex might stretch and contort the stars around you, creating an array of visual phenomena due to the warping of light. The experience inside the wormhole is theoretically instantaneous, yet profoundly disorienting. Due to the extreme gravitational forces, time itself could behave unpredictably. One might emerge on the other side having aged differently than observers who took a conventional route. However, the primary challenge lies in maintaining wormhole stability. Theoretical models often require exotic matter with negative energy density to hold the tunnel open, something not yet proven to exist. If humans ever harness the power to stabilize and navigate wormholes, it would mark a revolutionary leap in space exploration, rendering previously unreachable corners of the universe accessible and transforming our understanding of distance, time, and even causality. Oumuamua, which means scout or messenger in Hawaiian, made headlines in 2017 when it was identified as the first known interstellar object to visit our solar system. At approximately 400 meters long but only about 40 meters wide, its elongated cigar-like shape was unlike anything seen before. Adding to the mystery, Oumuamua exhibited unusual acceleration as it exited our solar system, deviating from the path predicted by simple gravitational theories. This mysterious behavior prompted a flurry of hypotheses concerning its nature and origin. Initially suspected to be a comet, Oumuamua lacked a visible tail or gas emissions typically associated with cometary bodies. Some scientists suggested it could be a fragment of a larger object, such as a planetesimal or asteroid, torn apart by gravitational forces in its home system. The peculiar acceleration sparked further speculation, leading some to propose more exotic explanations. One controversial hypothesis posited by a prominent physicist, Avi Loeb, is that Oumuamua could be an artificial object, possibly a light sail from an advanced extraterrestrial civilization. While there is no concrete evidence to support this, It underscores the enigma of Oumuamua and the limitations of our current understanding. Regardless of its true nature, this interstellar visitor has reignited scientific curiosity and underscored the vast, unexplored realms of our universe. Oumuamua's brief but enigmatic journey through our solar system serves as a poignant reminder of the cosmic mysteries that await discovery. Fast radio bursts, or FRBs, are one of the most perplexing phenomena in modern astrophysics. These incredibly brief but intense bursts of radio waves were first discovered in 2007, and they last only milliseconds. Despite their fleeting nature, the energy released in each burst is phenomenal, equivalent to what our sun emits in an entire day or even a year, depending on the FRB. The mystery deepens with the fact that these bursts come from distant galaxies, implying an extraordinary amount of energy must be involved to travel such cosmic distances. The precise origin and cause of FRBs remain hotly debated topics among scientists. One line of thought suggests that they could be the result of cataclysmic events like the collision of neutron stars or the collapse of massive stars into black holes. Such scenarios would explain the immense energy output, but would typically be one-time events. However, the discovery of repeating FRBs, such as FRB 121102, has compelled scientists to consider other explanations. Repeating FRBs might be caused by highly magnetized neutron stars, known as magnetars, which periodically release bursts of energy. Yet another tantalizing possibility, though speculative, is that FRBs could be artificial signals from advanced extraterrestrial civilizations using beams of energy for propulsion or communication. This is not the prevailing scientific view, but highlights the wide range of hypotheses driven by our limited understanding. Regardless of their true cause, FRBs challenge our understanding of the energetic processes in the universe and invite us to expand our scientific horizons. Each new detection adds another piece to this cosmic puzzle, beckoning further exploration and study that could eventually unlock profound truths about the universe. Rogue planets are enigmatic wanderers, having broken free from the gravitational embrace of any star, drifting alone through the cold, dark expanses of space. These wayward planets are thought to be as numerous as stars, yet their secrets remain largely hidden from us. With no parent star to provide warmth and light, these planets dwell in perpetual night, their surfaces reaching frigid temperatures far below what we can experience on Earth. Yet, the veil of darkness may conceal vibrant geological and possibly even biological processes. Beneath the icy exteriors of these rogue planets, geothermal activity could create subsurface oceans similar to those theorized on moons like Europa and Enceladus in our solar system. These hidden seas, warmed by internal heat from radioactive decay or from the aftermath of the planet's violent ejection from its home system, could potentially harbor microbial life. Life, after all, has proven resilient in extreme environments on Earth, such as hydrothermal vents at the bottom of our oceans. The absence of sunlight would not preclude life if these deep oceans have chemical energy sources, challenging our understanding of where life can take hold. Additionally, rogue planets could serve as cosmic time capsules, preserving evidence of their origins and the conditions of their former stellar systems. Study of these planets might reveal clues about planetary formation, migration, and the violent interactions leading to their solitary journeys. They also offer unique laboratories for studying planetary atmospheres without the confounding influence of stellar radiation. Unraveling the mysteries of rogue planets could thereby deepen our knowledge of planetary science and astrobiology. As our technology advances, the dark, drifting worlds that roam interstellar space may increasingly come into view, offering insights that could redefine our place in the cosmos. Neutron stars are extraordinary celestial objects that push the boundaries of our understanding of matter and physical laws. Born from the remnants of supernova, massive stars that exhausted their nuclear fuel and collapsed, these stars are incredibly dense. A neutron star packs a mass exceeding our sun's into a sphere only about 20 kilometers in diameter. 1 teaspoon of neutron star material would weigh around 1 billion tons on Earth, revealing extremes of density that defy our everyday experiences and challenge theoretical physics. Their extraordinary properties arise from the compression of atomic nuclei. Inside a neutron star, protons and electrons are forced so closely together that they merge to form neutrons, resulting in a state of matter known as neutron-degenerate matter. However, the star's core might conceal even more exotic states of matter. Some theories suggest the presence of quark-gluon plasma, where neutrons break down into their constituent quarks, or even more bizarre entities like strange matter, comprising strange quarks. These extreme conditions provide a natural laboratory to test and refine our theories of quantum mechanics and nuclear physics, which can't be replicated on Earth. Neutron stars also give rise to phenomena such as pulsars, a type of neutron star emitting beams of radiation that sweep across space like lighthouse beams, observable as regular pulses. The incredible rotational speeds of neutron stars, sometimes hundreds of times per second, coupled with their intense magnetic fields, trillions of times stronger than Earth's, make them sites of high-energy processes that challenge our understanding of electromagnetism and general relativity. The gravitational field around a neutron star is so fierce that it significantly warps space-time, providing insights into the curvature of space predicted by Einstein's theories. Studying these celestial titans not only enriches our understanding of how fundamental forces interact under extreme conditions, but also provides critical tests for theories that may one day unify all known forces of nature. Strange matter is an exotic form of matter composed of strange quarks, alongside the more familiar up and down quarks that make up protons and neutrons. Under normal conditions, strange quarks don't readily combine with others, but extreme environments, such as those found in neutron stars, might foster their formation. This theoretical state of matter is incredibly dense and stable and could provide new insights into the behavior of subatomic particles at energy levels far beyond what we can achieve in terrestrial laboratories. The concept of strange matter arises from the possibility that in the immensely dense cores of neutron stars, neutron-degenerate matter might transform into strange matter. If this occurs, it could lead to the formation of a strange star or quark star, which would be even denser than a typical neutron star. These hypothetical stars would have an extremely high binding energy, meaning they could potentially assimilate regular atomic nuclei into strange matter upon contact, resulting in stable states. If strange matter exists in the universe, it could drastically influence our understanding of stellar evolution and the life cycles of stars. The implications of discovering strange matter inside neutron stars would be profound. It would provide empirical evidence for theoretical physics models that predict its existence and validate the process of quark deconfinement under extreme pressures and temperatures. Such a discovery could also offer a unique window into the behavior of the strong nuclear force which binds quarks together under extreme conditions. Moreover, understanding strange matter could have cosmological implications, perhaps influencing the birth of neutron stars or the rates of supernovae. This exploration could alter our fundamental concepts of matter's stability and pave the way for future research into the nature of exotic states of matter in the universe. Dark matter is one of the most tantalizing mysteries in cosmology, constituting an estimated 85% of the universe's mass, yet it remains invisible and undetectable by conventional means. It does not emit, absorb, or reflect light, rendering it undetectable through traditional electromagnetic observations like those of stars and galaxies. However, its presence is inferred through its gravitational effects. For instance, the rotational speeds of galaxies and the way light bends around massive objects, a phenomenon known as gravitational lensing, cannot be explained by visible matter alone, indicating the presence of this unseen mass. To study dark matter, scientists have devised several ingenious methods. One approach involves direct detection experiments designed to observe potential interactions between dark matter particles and regular matter. These experiments typically occur deep underground to shield them from cosmic rays and other background interference. Detectors filled with supercooled liquids or solid-state targets await collisions with dark matter particles, which might produce minute flashes of light or vibrations. The Large Underground Xenon experiment, LUX, and its successors attempt just this by monitoring for rare events that could signal dark matter interactions. Another method is indirect detection, which looks for byproducts of dark matter annihilations or decays. Astrophysical observatories, both ground-based and space-based, search for excess gamma rays, neutrinos, or positrons that might originate from dense dark matter regions. Notable instruments in this field include the Fermi Gamma-ray Space Telescope and the Alpha Magnetic Spectrometer on the International Space Station. Additionally, particle accelerators like the Large Hadron Collider aim to recreate the conditions shortly after the Big Bang, potentially producing dark matter particles that can then be studied. Moreover, efforts in theoretical physics, such as simulations of dark matter's gravitational effects in large-scale structures of the universe, complement these experimental approaches. Advanced algorithms and computer models help to predict how galaxies form and cluster under the influence of dark matter, providing valuable insights that guide observational strategies. Ultimately, as our technological capabilities and theoretical understanding evolve, the elusive nature of dark matter will increasingly come under closer scrutiny, potentially leading to breakthroughs that could transform our understanding of the universe's fundamental composition and the forces that govern it. Magnetars are a fascinating and extreme subset of neutron stars distinguished by their incredibly powerful magnetic fields, which can be up to 1,000 times stronger than those of typical neutron stars. These magnetic fields, reaching up to a quadrillion, one followed by 15 zeros, times stronger than Earth's, could compress atoms and distort the very fabric of space around them. These conditions present unique opportunities to explore the mysteries of matter and the fundamental forces that govern it. One of the primary mysteries magnetars could help unravel involves the behavior of matter under extreme magnetic fields. In such intense fields, atomic structures could be drastically altered. Electrons might be forced into tight cyclotron orbits near the nucleus, leading to bizarre states of matter that differ significantly from those observed under standard conditions. Studying these effects could provide insights into quantum electrodynamics, QED, the quantum field theory describing interactions between light and matter under conditions that are impossible to replicate on Earth. Additionally, magnetars are sources of some of the most energetic phenomena in the universe, such as soft gamma-ray repeaters and anomalous X-ray pulsars. These high-energy emissions result from starquakes, crustal fractures caused by the intense magnetic stress and the subsequent release of magnetic energy. Observing these events can shed light on the dynamics of ultra-dense matter and the complex interactions between magnetic and crustal stresses. Another avenue of mystery lies in the potential existence of exotic particles or states of matter within magnetars. For instance, the intense conditions might facilitate the formation of quark matter, or even more exotic forms like strange matter inside these stellar remnants. Detecting unique signals or radiation emanating from these states could validate theories about the nature of matter at a fundamental level. Moreover, the intense magnetic fields themselves challenge and extend our understanding of magnetohydrodynamics, MHD, the study of the magnetic properties and behavior of electrically conducting fluids like plasmas. Magnetars are not just cosmic curiosities, but are crucial natural laboratories that push the limits of our understanding of matter, magnetic fields, and fundamental physics. Studying them can provide profound insights that bridge the gap between theoretical predictions and observable phenomena, potentially leading to new paradigms in astrophysics and particle physics. Hypervelocity stars are stellar speedsters, exceeding the typical velocities of stars in the Milky Way and sometimes reaching speeds that allow them to escape the galaxy entirely. These stars achieve their incredible velocities through highly energetic gravitational interactions. One compelling theory posits that they are accelerated by the supermassive black hole at the center of our galaxy, Sagittarius A star. When a binary star system ventures too close to this black hole, intense tidal forces can break it apart. One star is captured by the black hole, while its partner is flung away at tremendous speeds, sometimes exceeding several million kilometers per hour. Another scenario involves dynamic interactions in densely packed stellar environments like globular clusters or the remnants of supernova explosions. In these crowded arenas, close encounters between stars can result in significant gravitational slingshots, boosting some stars to hypervelocity. Supernovae can also contribute to this phenomenon. If one star in a binary system explodes, the surviving companion can be propelled at high speed due to the asymmetric explosion. The study of hypervelocity stars offers valuable insights into the structure and dynamics of our galaxy. By tracing their trajectories, astronomers can infer details about the distribution and density of dark matter in the Milky Way. These stars act as probes, offering a means to map out the gravitational potential of the galaxy, including the elusive dark matter halo that envelops it. Additionally, their origins help astronomers understand the processes occurring near the galactic center, providing clues about the behavior of objects in the extreme gravitational field of Sagittarius A star. Moreover, hypervelocity stars can also inform us about the history of stellar populations and star formation events in specific regions of the galaxy. Analyzing their compositions and ages can shed light on the conditions in which they formed and the subsequent dynamical processes that led to their ejection. Hypervelocity stars are cosmic messengers, carrying with them telltale signs of the gravitational dynamics, astrophysical processes, and unseen structures that shape our galaxy. The concept of alternate dimensions or parallel universes captivates both scientists and the general public alike. In theoretical physics, these notions are often explored within the frameworks of string theory, M theory, and the multiverse hypothesis. String theory, for instance, posits that the fundamental particles we observe are actually tiny vibrating strings that exist in a higher dimensional space, potentially encompassing up to 10 or 11 dimensions. While we experience the world in 3 spatial dimensions and 1 temporal dimension, these additional dimensions could be compactified or curled up in ways that make them imperceptible to us. Parallel universes, on the other hand, are suggested by the multiverse hypothesis. One version, the many worlds interpretation of quantum mechanics, proposes that every quantum decision spawns a new branching universe. In another version, known as the bubble universe theory, different regions of space could undergo inflation at different rates, creating isolated bubbles that develop into entirely separate universes. These universes could have different physical constants, making them vastly different from our own. Detecting alternate dimensions or parallel universes is a formidable challenge, but scientists are exploring a variety of ingenious methods. High-energy particle collisions, such as those conducted at the Large Hadron Collider (LHC), could provide clues. If extra dimensions exist, they might manifest themselves through missing energy and momentum in particle reactions, suggesting that particles are leaking into these unseen dimensions. Additionally, subtle gravitational effects, detectable through advanced instruments like gravitational wave observatories, might reveal the presence of extra dimensions or neighboring universes. Cosmological observations also offer potential insights. Variations in the cosmic microwave background radiation, the afterglow of the Big Bang, could carry imprints of interactions with other universes or higher dimensions. Anomalies or irregularities in this radiation might signal such interactions. Similarly, the study of dark matter and dark energy could reveal phenomena that are best explained by influences from extra dimensions or other universes. Though these ideas push the boundaries of contemporary science, they inspire innovative experiments and observations that continuously refine our understanding of the universe. If proven, the existence of alternate dimensions or parallel universes would revolutionize our perception of reality, expanding the horizon of what the universe is and could be. As our technological and theoretical tools advance, the quest to uncover these hidden realms continues to stir intrigue and fuel scientific exploration. The multiverse theory suggests that our universe might be just one of an enormous, possibly infinite number of universes that exist simultaneously. While this idea remains speculative and deeply theoretical, there are tantalizing hints and frameworks in modern physics that lend it some credibility. One of the most significant pieces of indirect evidence comes from the field of cosmology, particularly the theory of cosmic inflation. Cosmic inflation posits that a rapid expansion of space occurred just fractions of a second after the Big Bang. This inflationary process could have produced multiple separate bubble universes, each with its own unique properties and laws of physics. Quantum mechanics also provides a basis for multiverse theories. The many worlds interpretation of quantum mechanics proposes that every quantum event spawns a new branching universe where all possible outcomes of that event occur. This interpretation, though not universally accepted, offers a compelling explanation for the probabilistic nature of quantum phenomena. In addition to these theoretical frameworks, there are observational hints that might suggest a multiverse. For example, anomalies in the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, could potentially be signatures of interactions between our universe and others. Some scientists have even speculated that unusual cold spots in the CMB might be evidence of past collisions with other universes. However, these interpretations are highly contentious and require much more data and rigorous testing to be substantiated. The implications of the multiverse theory are profound and far-reaching. If our universe is just one of many, it challenges the notion of a unique single reality and suggests that there could be myriad versions of events, histories, and existences. This could fundamentally alter our understanding of causality and the nature of existence itself. It would also provide a context for explaining why our universe appears fine-tuned for life. If there are countless universes with varying conditions, it's not surprising that at least one, ours, has the right conditions for life to emerge. Furthermore, the acceptance of a multiverse could lead to breakthroughs in many fields of physics, offering new insights into the fundamental forces and particles that govern our universe. It could also help reconcile discrepancies between quantum mechanics and general relativity, two pillars of modern physics that remain stubbornly incompatible. While the multiverse theory remains speculative, ongoing advancements in observational technology and theoretical models could one day provide more tangible evidence. Until then, it remains a fascinating and provocative idea that stretches the boundaries of our understanding and invites us to ponder the very nature of reality itself. The holographic principle is a radical and intriguing idea in theoretical physics that suggests the entire universe can be described as a two-dimensional information structure painted on the cosmological horizon. This proposition challenges our deeply held intuition that we inhabit a three-dimensional space. Originating from insights into the behavior of black holes, the holographic principle was formulated to resolve paradoxes concerning the nature of information and entropy in such dense objects. The principle gained traction from the work of physicists like Gerard de 't Hooft and Leonard Susskind, who drew analogies from Stephen Hawking's discovery that black holes emit radiation and subsequently lose mass, leading to the so-called information paradox. According to conventional understanding, information about the physical state of objects falling into a black hole would be lost as the black hole evaporated, violating principles of quantum mechanics that assert information must be conserved. The holographic principle resolves this by suggesting that all the information about the three-dimensional interior of the black hole can be encoded on its two-dimensional event horizon. Extending this concept to the entire universe, the holographic principle posits that the physics within our three-dimensional universe is fully described by information on a distant, two-dimensional surface. In this view, our perception of volume and depth is akin to a hologram, where a three-dimensional image can be reconstructed from two-dimensional data. This paradigm suggests that the fundamental essence of reality may be information itself, encoded on a lower dimensional boundary. Adopting the holographic principle challenges and reshapes our understanding of space, time, and the nature of reality. It implies that the richness and complexity of our spatial experience are emergent phenomena from this more fundamental informational substrate. This concept could have profound implications for the unification of quantum mechanics and general relativity, prompting new lines of inquiry into the very fabric of space-time and gravitational interactions. Testing the holographic principle experimentally remains a substantial challenge, but areas of ongoing research include the study of the ADES-CFT, anti-de Sitter space conformal field theory, correspondence, a concrete realization of the holographic principle proposed by Juan Maldacena. This framework provides a powerful tool for exploring quantum gravity and has yielded insights into various physical processes, from black hole thermodynamics to quantum field theories. Ultimately, if the holographic principle holds true, it would represent one of the most profound paradigm shifts in our understanding of the universe. It invites us to reconsider the nature of dimensions and the foundational elements that constitute reality, potentially offering a pathway to reconcile some of the deepest mysteries in theoretical physics. The proposition that our universe could be a giant simulation, often referred to as the simulation hypothesis, has profound implications for our understanding of reality, ethics, and the nature of existence. This idea, popularized by philosophers like Nick Bostrom, suggests that all of our experiences, the laws of physics, and the universe itself might be the product of massive computational processes running on an advanced civilization's hardware. One of the most immediate implications of the simulation hypothesis concerns the nature of reality itself. If we live in a simulated universe, then what we perceive as physical reality is essentially an elaborate construct, much like the pixels on a screen form images, but have no inherent reality itself. If we live in a simulated universe, then what we perceive as physical reality is essentially an elaborate construct, much like the pixels on a screen form images, but have no inherent reality of their own. This would imply that the fundamental particles, forces, and constants we study are part of a sophisticated program designed to mimic the complexity and richness of an authentic universe. Philosophically, it challenges the notion of objective reality and pushes us to consider reality as fundamentally informational. Ethically, the simulation hypothesis raises questions about the moral status and meaning of our actions. If we are in a simulation, does it diminish the significance of our experiences or the value of human life? Some argue that whether simulated or not, our subjective experiences are real to us, and thus our actions and ethical considerations retain their importance. Others ponder the ethical obligations of the simulators. If they created our universe, do they have a responsibility toward us, and how might such considerations influence our behavior and values? The hypothesis also raises intriguing questions about determinism and free will. If our universe is a simulation, it might be governed by a set of predetermined codes and algorithms, suggesting a form of hard determinism. On the other hand, the simulators could program for emergent phenomena and randomness, allowing for a semblance of free will and spontaneity within the constraints of the simulation's rules. Detecting whether our universe is a simulation poses significant theoretical and experimental challenges. Some scientists have speculated about possible signatures or anomalies in the structure of the universe that might hint at underlying code. For instance, pixelation at the smallest scales of spacetime or irregularities in the cosmic microwave background. Others have suggested that high-energy physical processes at the quantum level could reveal inconsistencies if they deviate from what we expect in a base reality. Finally, embracing the simulation hypothesis could alter our existential perspective. It might prompt us to explore the nature and purpose of the simulation itself. Are we an experiment, an entertainment, or are we progenitors of our own future simulations? Such considerations expand the scope of our inquiry beyond traditional scientific and philosophical boundaries, inviting us to contemplate the ultimate questions of our origin, purpose, and destiny in a potentially infinite cascade of simulated realities. Whether true or not, the simulation hypothesis serves as a powerful thought experiment, challenging us to rethink the foundations of knowledge, reality, and existence, and urging us to explore the depths of what it means to be conscious beings in a possibly simulated cosmos. Imagine two particles intertwined in such a manner that the state of one instantaneously determines the state of the other, even if they are separated by astronomical distances. This phenomenon, known as quantum entanglement, has perplexed scientists since it was first theorized by Albert Einstein, who referred to it as spooky action at a distance. Experiments have shown that changes to the properties of one entangled particle are reflected in its partner, regardless of how far apart they are. This defies the conventional understanding of physics, where information should not travel faster than the speed of light. Now let's take a leap into the speculative but intriguing realm of interconnected universes. If our universe is just one of many, as suggested by the multiverse theory, quantum entanglement might be the thread that connects these diverse realms. While still a topic of theoretical exploration, some physicists hypothesize that entangled particles could be linked across different universes. This opens the tantalizing possibility that actions in one universe could have mirrored consequences in another. Observing such phenomena could provide indirect evidence of these parallel universes, challenging our existing notions of reality and forcing us to reconsider the very fabric of space and time. In this way, The enigmatic dance of entangled particles presents not just a puzzle, but a potential gateway to uncovering the profound architecture of the cosmos. Located approximately 150 million light-years away in the direction of the constellation Centaurus, the Great Attractor is an enigmatic region in space, exerting a gravitational force so powerful that it's pulling our own Milky Way galaxy, along with thousands of others, toward it. Despite its immense influence, the exact nature of the Great Attractor remains shrouded in mystery, largely because it's situated in a part of the sky obscured by our galactic plane, making it near impossible to study with traditional telescopes. What could be hiding in the depths of this cosmic enigma? Some scientists speculate that the Great Attractor could be a colossal accumulation of dark matter, an invisible substance that doesn't emit light, but makes up about 27% of the universe's mass energy content. If true, studying it could unravel the secrets of dark matter, amplifying our understanding of one of the most perplexing phenomena in cosmology. Alternatively, this region might host an unusually dense supercluster of galaxies, an assembly so massive that its combined gravitational pull outshines anything we've encountered thus far. Unlocking the mysteries of the Great Attractor might not just answer a single question, it could illuminate the myriad forces shaping the grand architecture of our universe. The idea that the universe might have a boundary is both tantalizing and bewildering. Traditional cosmological theories suggest the universe is finite yet unbounded, akin to the surface of a sphere. In this analogy, traveling in one direction indefinitely would eventually bring you back to your starting point. This concept stems from the principles of general relativity, which describe the universe's curvature and topology. However, if the universe does have a boundary, it fundamentally challenges our understanding of space-time and raises profound questions about what lies beyond. One speculative concept is that beyond such a hypothetical boundary could exist the multiverse, an ensemble of multiple, perhaps infinitely many universes. Each universe within this multiverse might follow different physical laws, constants, and dimensions, making them incomprehensible from our point of view. Another possibility is that beyond the universe lies a higher dimensional space, often referred to in theoretical physics as hyperspace. This could be a dimension we cannot perceive directly, but influences the structures and behavior of our universe. These ideas remain in the realm of theoretical conjecture and mathematical models, as currently we lack the empirical means to explore such boundaries. Nonetheless, contemplating what might exist beyond our universe uncovers deep philosophical and scientific inquiries, inviting us to rethink the very nature of existence and the limits of human comprehension. Cosmic inflation is a revolutionary concept that fundamentally reshapes our understanding of the early universe. Proposed in the early 1980s by physicist Alan Guth, the idea suggests that a fraction of a second after the Big Bang, the universe experienced an exponential expansion, growing from subatomic scales to astronomical sizes in a blink of an eye, specifically in about 1/1,000,000,000 of a trillionth of a trillionth of a second. This rapid inflation smoothed out the irregularities and homogenized the energy distribution, setting the stage for the formation of galaxies, stars, and ultimately, all cosmic structures. This concept addresses several vexing issues in cosmology. One major conundrum it resolves is the horizon problem, which asks why, despite being 13.8 billion years old, the universe is so uniform in temperature and density, even in regions too far apart to have ever been in causal contact. Inflation explains this by positing that these distant regions were once close together before the exponential expansion stretched them far apart. Moreover, inflation provides a mechanism for the flatness problem, explaining why the universe appears to be geometrically flat rather than curved. Probing the precise parameters and implications of this inflationary epoch continues to be a major focus in cosmological research, using tools like the cosmic microwave background radiation, which carries the faint afterglow of this tumultuous period. By understanding cosmic inflation, we get closer to piecing together the dawn of time and the very blueprint of our universe. In the speculative Big Rip scenario, the universe's accelerating expansion, driven by a mysterious form of energy known as dark energy, could eventually become so dominant that it tears apart all cosmic structures. This cataclysmic sequence begins inconspicuously, with galaxies moving away from each other at an ever-increasing pace. As time progresses, the expansion force would surpass the gravitational bindings of galaxies, causing them to disintegrate. As the acceleration intensifies, the next victims would be star systems, with stars and planets drifting apart as the bonds holding them together are overwhelmed. Eventually, the very atoms constituting matter could be torn asunder as the overwhelming force shatters electrons from nuclei, breaking down the fabric of matter itself. In the terminal moments of the Big Rip, even space and time may be stretched to their limits and fragmented into nothingness. This harrowing scenario, while largely theoretical, propels significant investigations into the nature of dark energy and the ultimate fate of our universe. Understanding the true behavior of dark energy is crucial, as it governs whether the cosmos ends in a gentle fade, a cataclysmic collapse, or this dramatic and devastating Big Rip. The notion of multiple universes, each with its own unique set of physical laws, is a captivating aspect of the multiverse theory. If other universes do exist, they could diverge from ours in unimaginable ways owing to variations in fundamental constants, dimensions, and natural laws. For instance, consider a universe where the gravitational constant is significantly stronger or weaker than in our own. In a universe with stronger gravity, stars might burn out much faster, collapsing into black holes with alarming rapidity, potentially preventing the formation of stable planetary systems and inhibiting the development of life as we know it. Alternatively, a universe governed by different quantum laws could present a reality where the building blocks of matter are differently configured. Elements and chemical reactions, the very basis of biology and chemistry, might be completely alien to us. In some hypothetical universes, dark energy could be repulsive enough to disrupt the cohesion of atoms, making solid matter an impossibility. Conversely, if dark energy is non-existent or behaves differently, these universes might experience eternal stasis or endless cycles of collapse and rebirth, akin to a cosmic phoenix. Imagining these diverse universes pushes the boundaries of our comprehension and provides a profound perspective on the unique conditions that allowed life and structure to arise in our own universe. These speculative realms highlight the fine-tuned nature of our cosmic habitat, amplifying the mystery of why our universe possesses precisely the laws and constants that it does, a question that continues to provoke deep scientific and philosophical inquiry. The dark flow is an intriguing and somewhat enigmatic phenomenon first identified by astronomers in 2008. It describes the peculiar, coherent motion of galaxy clusters traveling at a significant speed of about 1 million miles per hour in a specific direction toward a patch of sky near the constellations Centaurus and Hydra. This motion is perplexing because it contradicts the expected random dispersal patterns dictated by known gravitational forces and the cosmic microwave background radiation, which is the afterglow of the Big Bang. One provocative explanation for the dark flow is the gravitational influence exerted by structures beyond the observable universe, possibly hinting at the existence of other universes. These structures could be part of a larger multiversal framework, where our universe is just a small segment of a more extensive cosmic living room. If there are other universe-like entities exerting gravitational pulls from beyond the observable edges, it could explain why vast regions of galaxy clusters exhibit this inexplicable flow. This hypothesis extends the boundaries of our understanding of cosmology, suggesting that our universe might be only one bubble in a frothing sea of countless other bubbles. While definitive proof remains elusive, the dark flow phenomenon propels us to contemplate the far-reaching implications of the multiverse theory, opening up possibilities that transcend the observable limitations of our cosmic horizon. The Big Bounce theory posits a fascinating alternative to the more traditional Big Bang cosmology, suggesting that our universe is the latest in an eternal series of cyclical expansions and contractions. According to this hypothesis, the universe begins with a Big Bang, expands over billions of years, and eventually, due to gravitational forces or other mechanisms, slows down and starts contracting in a process known as the Big Crunch. Instead of ending in a singularity, this contraction reaches a critical point where a rebound occurs, leading to another Big Bang and the birth of a new universe. This cycle of births, expansions, contractions, and rebirths continue infinitely. What's intriguing about the Big Bounce theory is how it integrates principles from quantum mechanics and general relativity to explain the cosmos's behavior under extreme conditions. Near the point of maximum contraction, quantum gravitational effects become significant, potentially preventing a total collapse into a singularity. Instead, these effects could generate a repulsive force sufficient to trigger a new expansion phase. If the theory holds true, remnants of previous cosmological cycles, perhaps encoded in cosmic microwave background variations or gravitational waves, could offer insights into the universe's pre-bounce state. This cyclical model paints a profound narrative of cosmic eternity, where each cycle resets the cosmic stage for a new act. It challenges the conventional view of a single, linear evolutionary timeline for the universe and suggests that existence is an endless loop of destruction and renewal. Exploring the Big Bounce opens the door to deeper inquiries about the nature of time, space, and the fundamental forces that govern the cosmos, forging connections between the quantum underpinnings of the universe and the grand scale of cosmic evolution. The ekpyrotic model presents a radical departure from traditional cosmological theories by suggesting that our universe was birthed from the collision of immense, higher-dimensional objects known as brains. Originating from string theory, this concept posits that our universe exists on a three-dimensional brain, which moves within a higher-dimensional space, often referred to as the bulk. The hypothesis is that periodically our brain collides with a parallel brain, and the immense energy released during these collisions initiates a Big Bang-like event, giving rise to a new universe. This model has several profound implications for our understanding of cosmology and the fundamental workings of the universe. Firstly, it provides an intriguing alternative to cosmic inflation, offering a different explanation for why the universe appears so flat and uniform. Unlike inflation, which posits a rapid expansion to smooth out the universe, the ekpyrotic model suggests that the pre-collision high temperatures and densities naturally homogenize the universe. Additionally, this model merges the realms of quantum mechanics and general relativity, providing a framework where the cyclic nature of brain collisions could potentially explain the sequence of Big Bangs and Big Crunches observed throughout cosmic history. Furthermore, the ekpyrotic universe opens the door to the fascinating possibility of parallel universes existing on adjacent branes, only a slight nudge away in higher dimensions. These universes could vary dramatically in their physical laws and constants, challenging our notions of what is possible within reality. Testing the ekpyrotic model involves searching for distinct signatures in the cosmic microwave background radiation or gravitational waves that could differentiate it from other cosmological models. By exploring the ekpyrotic scenario, scientists delve into the intricate dance of dimensions and branes, potentially uncovering a far richer understanding of the cosmos and its origins than previously imagined. String theory is a compelling framework that aims to unify the four known fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single coherent theory. At its core, string theory proposes that the fundamental building blocks of the universe are not point-like particles as traditionally thought, but rather tiny vibrating strings of energy. These strings can loop and oscillate in various modes, with each mode representing a different particle. The beauty of this approach lies in its potential to harmonize the currently disjointed frameworks of quantum mechanics, which governs the microcosm of particles and forces, and general relativity, which describes the macrocosm of gravitational interactions. One of the most significant aspects of string theory is its requirement for additional spatial dimensions beyond the familiar 3 dimensions plus time. In most string theory models, there are 10 or even 11 dimensions, with the extra dimensions compactified or curled up so small that they are imperceptible at human scales. These additional dimensions allow string theory to incorporate gravity in a natural way. Unlike quantum field theories that struggle to quantize gravity without resulting in nonsensical infinities, string theory's extended framework can accommodate the graviton, the hypothetical quantum particle of gravity, arising from a specific vibrational mode of a string. String theory also introduces the concept of supersymmetry, which posits that every known particle has a superpartner particle. This idea helps to ameliorate certain theoretical issues, such as the hierarchy problem, making the unification of forces more seamless. Experimental verification remains a major challenge, as direct evidence for strings or extra dimensions is currently beyond our technological reach. Nonetheless, string theory's mathematical elegance and potential to unify all forces provide a tantalizing glimpse into a world where all of nature's diversities are manifestations of a single, underlying essence. Exploring this unification could revolutionize our understanding of the cosmos, leading to a theory of everything that ties together the grand tapestry of reality. Loop quantum gravity, LQG, is a cutting-edge theoretical framework that seeks to harmonize the seemingly incompatible realms of quantum mechanics and general relativity. Traditional views of space-time, as formulated by Einstein, describe it as a smooth, continuous fabric that can be warped by the presence of mass and energy. However, LQG challenges this conception by proposing that space-time itself is fundamentally discrete, composed of tiny quantized loops called spin networks or spin foam. These loops are incredibly small, on the order of the Planck length, around 10 circumflex 35 meters, which is far smaller than anything we can currently observe directly. The granularity of space-time in LQG implies that at the most microscopic scales, the smooth geometry we're accustomed to breaks down into a web of interconnected loops, much like a woven fabric. This discrete structure allows LQG to avoid the singularities and infinities that plague general relativity when applied to the quantum scale, such as those at the center of black holes or the initial conditions of the Big Bang. Instead of a singularity, LQG predicts a quantum bounce, where the extreme curvature leads to a new expanding phase, a concept reminiscent of but distinct from the Big Bounce theory. One of the most intriguing implications of LQG is its potential to explain the quantum properties of black holes, including the preservation of information, which addresses the perplexing paradoxes that arise in black hole thermodynamics. By quantizing areas and volumes, LQG provides a framework for calculating the entropy of black holes in a way that aligns with holographic principles. Though still in its developmental stages and facing significant experimental hurdles, loop quantum gravity offers a radically new perspective on the nature of spacetime, pushing the frontier of physics toward a deeper understanding of the universe's foundational constituents. If proven, it could revolutionize the way we perceive space, time, and reality itself, merging the macroscopic world of relativity with the microscopic quantum realm into a unified tapestry. The anthropic principle is a thought-provoking concept that attempts to explain why the universe appears to be meticulously fine-tuned to support life, particularly human life. At its core, the principle posits that the physical universe must be compatible with the conscious beings who observe it, essentially arguing that the universe's laws, constants, and fundamental parameters are such that they allow for the emergence of life because, if they weren't, we wouldn't be here to notice them. This principle comes in two primary forms: the weak and the strong anthropic principles. The weak anthropic principle suggests that the universe's observed values of physical constants are not particularly surprising because only those values which permit the existence of observers can actually be observed. For instance, if the gravitational constant were weaker or stronger by even a small fraction, galaxies, stars, and planets might never have formed, making the development of life as we know it impossible. Therefore, it's not astonishing that we find ourselves in a universe with the precise conditions necessary for our existence. We couldn't exist in any other kind. On the other hand, the strong anthropic principle ventures further by proposing that the universe must have properties that allow life to develop at some stage in its history, essentially suggesting that the cosmos is somehow designed with life in mind. This version sparks deeper philosophical and metaphysical inquiries, raising questions about whether there could be multiple universes, each with different constants and laws, as posited by the multiverse theory, or whether some form of higher purpose or design might be at play. Overall, the anthropic principle pushes us to contemplate the astonishing alignment of conditions that permit life in the universe. While not a scientific explanation in itself, it underscores the significance of the parameters that govern the cosmos, driving scientists and philosophers alike to explore why the universe is the way it is and whether our existence is merely a fortunate accident in an infinity of possible realities. Modified Newtonian dynamics, MOND, is a novel theoretical framework proposed by physicist Mordechai Milgram in the early 1980s as an alternative to the dark matter hypothesis. Dark matter has been invoked to explain various astronomical observations, such as the anomalous rotational speeds of galaxies, which cannot be accounted for solely by the visible matter and Newton's laws of gravity. Instead of positing an unseen, invisible form of matter, MOND suggests that the laws of gravity themselves might differ at very low accelerations, specifically in the regime encountered in the outskirts of galaxies. In MOND, the classical Newtonian theory is modified when the acceleration due to gravity falls below a specific threshold, approximately 0.01 nanometers per second squared. At these extremely low accelerations, the force of gravity does not diminish with the square of the distance as Newton's law dictates, but instead follows a weaker inverse linear law. This modification can explain the flat rotation curves of galaxies without requiring dark matter. The rotational speeds of stars at the edges of galaxies can be consistent with the amount of visible matter present when this revised gravity law is applied. Though intriguing, MOND faces significant challenges. While it provides a compelling explanation for galactic rotation curves, it has difficulty accounting for other phenomena attributed to dark matter, such as the gravitational lensing observed in galaxy clusters and the large-scale structure of the universe. Additionally, MOND struggles to align with the highly successful framework of general relativity, particularly in describing cosmological events such as the cosmic microwave background radiation. Despite these challenges, MOND remains an active field of research and has spurred further refinement and hybrid theories, such as relativistic MOND, or TVES, tensor vector scalar gravity, which attempt to bridge the gap between MOND's predictions and observations in both galactic and extragalactic contexts. By questioning the foundational laws of gravity, MOND invites us to reconsider our understanding of the cosmos, potentially unlocking new paths to resolve the dark matter enigma or even leading to a more comprehensive theory of gravity itself. Primordial black holes, PBHs, are a fascinating and somewhat controversial concept that proposes the existence of black holes formed in the very early universe, mere moments after the Big Bang. Unlike conventional black holes, which result from the gravitational collapse of massive stars at the end of their life cycles, PBHs could have formed from the immense density fluctuations in the rapidly expanding, hot and dense early universe. These fluctuations could have caused regions of space to collapse under their own gravity, forming black holes of varying sizes, from microscopic scales to masses many times that of our Sun. The existence of PBHs could significantly challenge and expand our understanding of the early universe and its development. For instance, they offer a potential explanation for some of the dark matter that makes up approximately 27% of the universe's mass-energy content. Current dark matter theories rely on weakly interacting massive particles, WIMPs, that haven't yet been detected despite extensive searches. PBHs, being purely gravitational, could constitute part or all of the dark matter, thus providing an alternative to particle-based explanations. Furthermore, PBHs could influence various phenomena observed in the universe today. Their presence could affect the formation of galaxies and large-scale structures by providing additional seeds for gravitational attraction. They might also be responsible for some of the gravitational wave signals detected by observatories like LIGO and Virgo, particularly those involving mergers of black holes with unexpected masses. Additionally, the study of PBH touches on fundamental questions about the nature of quantum gravity and the interplay between quantum mechanics and general relativity. If PBHs were formed, they might carry imprints from the high-energy laws governing the universe shortly after the Big Bang, providing clues about physics at energy scales far beyond those accessible in our current particle accelerators. While the evidence for PBHs is still indirect, and their existence remains a topic of vigorous debate, their potential to reshape our understanding of cosmology and the fundamental forces of nature makes them a captivating area of research. Whether or not they exist, the exploration of PBHs pushes us to contemplate the complexities of the early universe and the mysterious dark matter that pervades it, bringing us closer to a more comprehensive picture of the cosmos. The concept of baryon asymmetry delves into one of the most perplexing questions in cosmology and particle physics. Why does the universe contain more matter than antimatter? According to the standard model of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other, converting into energy. However, the observable universe is overwhelmingly composed of matter, with very little antimatter detected, suggesting some asymmetry developed early in the universe's history. This imbalance, known as baryon asymmetry, is crucial because it explains the very existence of galaxies, stars, planets, and ultimately us. If matter and antimatter were produced in perfectly equal quantities, they would have annihilated each other completely, leaving behind a universe filled only with radiation. The fact that this annihilation did not occur implies that there was a slight excess of matter over antimatter, about one extra baryon, a class of particles that include protons and neutrons, for every billion baryon-antibaryon pairs in the primordial universe. Various mechanisms within the realm of particle physics have been suggested to fulfill these conditions, such as interactions involving the Higgs boson, or hypothetical particles like axions or sterile neutrinos. Further, the phenomenon of CP violation has been observed in certain particle interactions, but not to the extent required to account for the observed asymmetry. The significance of baryon asymmetry extends beyond merely explaining the predominance of matter. It has profound implications for our understanding of the fundamental forces and the early universe's conditions, providing insights into physics beyond the standard model. As we continue to explore this enigma through experiments in particle accelerators, observations of cosmic microwave background radiation, and studies of high-energy astrophysical phenomena, each finding brings us a step closer to unraveling this fundamental mystery of why the universe, as we know it, exists at all. The holographic universe theory, a tantalizing concept in modern cosmology, posits that the entire three-dimensional universe we perceive, with its seemingly vast expanses of space and infinite depth, might actually be an illusion projected from information stored on a two-dimensional surface. This idea originates from the work of physicist Gerard T. Hooft in the 1990s, later expanded upon by Leonard Susskind. The theory can be best understood by imagining a hologram. If you've ever marveled at one, you'll know that it's a 2D image that encodes 3D information. Likewise, the theory suggests that all particles, forces, and even the very fabric of space-time might derive from data inscribed on a distant, cosmological boundary. Recent scientific developments bolster this intriguing notion. Studies of black holes provided a springboard for these ideas. When matter falls into a black hole, the information about that matter isn't lost but rather scribed onto the event horizon's surface, a 2D boundary. By analogy, our universe might function similarly. Entropy and information theory also play crucial roles in this hypothesis by suggesting that the maximum amount of information a region of space can contain is proportional to its surface area, not its volume. Essentially, although we live within a perceivable 3D reality, the underlying blueprint governing all cosmological phenomena might exist on a flat two-dimensional canvas, complicating yet fascinatingly enriching our understanding of the cosmos. Life on a planet orbiting a pulsar would be a scenario unlike anything we are familiar with on Earth. Pulsars, the remnants of supernova explosions, are highly magnetized rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. These beams sweep through space like cosmic lighthouses, and the radiation is extraordinarily intense. Any planet in the vicinity would be bombarded by high-energy gamma rays and X-rays, making the surface conditions extremely hostile to life as we know it. However, fascinatingly, hypothetical forms of life could adapt or evolve to survive in such an extreme environment. Shielding mechanisms would be vital for survival. For instance, life forms might reside deep below the surface, akin to extremophiles on Earth that live miles underground or in deep ocean vents, to protect themselves from the deadly radiation. Additionally, the planet would likely require an exceptionally thick atmosphere or magnetic field to deflect a portion of the pulsar's radiation. This atmosphere might be composed of dense layers of heavy gases, providing a shield and absorbing much of the radiation before it could reach the surface. The rhythm of life would be starkly different, potentially synchronized with the pulsar's pulsation periods, which can range from milliseconds to seconds. Every pulse, a tidal wave of energy, could impact the planet's atmosphere and magnetic fields, creating dynamic and possibly hazardous living conditions. Adaptation strategies might include extreme forms of radiation resistance, rapid DNA repair mechanisms, and life cycles tightly bound to periods of lower radiation intensity. Though speculative, this paints a picture of resilience and adaptability in the face of one of the universe's most formidable environments. A planet with a permanent day side and night side, often referred to as a tidally locked planet, presents a unique environment for potential life forms. Tidally locked planets have one side perpetually facing their star, bathed in constant daylight, while the opposite side remains in unending darkness. This creates a diverse range of climatic and ecological zones that could support various forms of life, each adapted to the distinct conditions of their specific region. On the day side, the intense and uninterrupted sunlight could lead to scorching temperatures, driving any potential life to adapt in fascinating ways. Organisms here might evolve reflective or heat-dissipating features to manage the extreme heat, similar to certain desert creatures on Earth. It is also plausible that life would be concentrated in regions where high albedo surfaces, such as ice or desert sands, reflect more sunlight, thereby lowering surface temperatures and creating more hospitable microenvironments. Photosynthetic organisms might flourish in areas with abundant light, perhaps evolving to store energy efficiently to cope with temperature fluctuations and periodic resource scarcity. In stark contrast, the night side would be enveloped in perpetual darkness and bitter cold. Here, life forms might rely on chemosynthesis or geothermal energy rather than sunlight to thrive, somewhat resembling the extremophiles found in Earth's deep ocean vents. These organisms could develop bioluminescence, not only for visibility but also as a means to attract mates or prey. The most promising region for life on such a planet might actually be the twilight zone, the narrow band between the day and night sides, where temperatures could be relatively mild and stable. Here, organisms could exist within a temperate climate, possibly similar to the more extreme environments on Earth. This area could harbor a diversity of life forms, from those that bask in the faint twilight to those that venture into the neighboring extremes to gather resources. The unique conditions on a tidally locked planet would undoubtedly foster highly specialized and adaptive life forms, resulting in an ecosystem as complex and wondrous as our own. Hot Jupiters are a class of exoplanets that orbit extremely close to their parent stars, often completing an orbit in just a few days. These planets are similar in composition and size to Jupiter in our solar system, but the key difference lies in their proximity to their stars. Imagine a gas giant like Jupiter, but orbiting closer to its star than Mercury does to our Sun. This proximity results in surface temperatures on these planets soaring into the thousands of degrees Fahrenheit, hence the name Hot Jupiters. The existence of hot Jupiters posed a considerable challenge to conventional planetary formation theories when they were first discovered. According to the widely accepted model of planetary formation, gas giants form in the cooler, outer regions of a protoplanetary disk, far from the intense heat of a young star. Over time, these gas giants accumulate a substantial atmosphere from the abundant hydrogen and helium present in these outer regions. However, the discovery of hot Jupiters defied this model since their presence so close to their stars suggested either a fundamentally different formation process or significant post-formation migration. Current theories hypothesize that hot Jupiters initially form in these distant, colder regions and then migrate inward through various potential mechanisms. One possibility is that gravitational interactions with the disk itself, or with other forming planets, could cause these giants to spiral inward over time. Another possibility involves interactions with a secondary star in a binary system that could perturb the gas giant's orbit, causing it to move closer to its primary star. This inward migration would need to occur relatively quickly on an astronomical timescale to avoid the gas giant falling into the star or being disrupted by its gravitational forces. Thus, hot Jupiters have not only expanded our understanding of planetary systems, but also forced astronomers to refine and complicate the models of how planets grow and evolve around their stars. Super-Earths are a fascinating category of exoplanets that have garnered significant attention since their discovery. These planets are larger than Earth, but significantly smaller than the ice giants Uranus and Neptune in our solar system, typically ranging from 1 to 10 times the mass of Earth. The existence of super-Earths has broadened our perspective on planetary diversity and habitability, challenging our previous notions that were largely based on the planets within our own solar system. One of the ways super-Earths expand our understanding is by presenting a new spectrum of planetary characteristics that sit between terrestrial planets like Earth and gas giants like Jupiter. These planets often possess thick atmospheres, diverse geological activity, and perhaps even vast oceans, each of which offers unique conditions that could support life. Because they are more massive than Earth, super-Earths may have stronger gravitational fields, which can retain thicker atmospheres and potentially regulate more stable climates. Furthermore, their increased size could promote tectonic activity, which is crucial for recycling essential elements and maintaining planetary habitability over geological timescales. The study of super-Earths also pushes the boundaries of the habitable zone concept, the range of distances from a star where liquid water could exist on a planet's surface. Some super-Earths might have the right conditions even if they lie outside the traditional habitable zone due to their potential for generating internal heat through tidal forces or radiogenic decay. This internal heating could sustain subsurface oceans, similar to the conditions believed to exist on moons like Europa and Enceladus in our solar system. By expanding what we consider the habitable zone, super-Earths open up a greater variety of environments where life might thrive, suggesting that habitable planets might be more common than previously thought. Moreover, the diversity of super-Earths helps astronomers refine models of planet formation and evolution. By studying their atmospheres, compositions, and orbital dynamics, we gain valuable insights into how planets accrete material, differentiate their interiors, and interact with their parent stars and sibling planets. The presence of super-Earths around different types of stars, from stable G-type stars like our Sun to more volatile M-dwarfs, adds layers of complexity and richness to our understanding of planetary systems, offering myriad possibilities for future exploration and the tantalizing hunt for extraterrestrial life. Ice giants such as Uranus and Neptune present some of the most intriguing mysteries in planetary science, challenging our comprehension of how planets form and evolve. Unlike the gas giants Jupiter and Saturn, which are primarily composed of hydrogen and helium, Uranus and Neptune have significant amounts of heavier elements like water, ammonia, and methane, forming complex layers of icy and rocky materials beneath their thick atmospheres. This distinct composition provides critical clues about the varied processes that govern planetary formation. One of the enduring mysteries of ice giants lies in their formation mechanisms. According to current models, these planets likely formed further out in the protoplanetary disk, where ices and heavier elements are more abundant. However, the exact process of their formation remains debated. There's a hypothesis that Uranus and Neptune could have initially formed as smaller cores that gradually accumulated icy and rocky material. Alternatively, they might have undergone rapid accretion, capturing significant amounts of gas and ice before migrating inward to their present positions. The migration theory is particularly intriguing as it suggests these planets could have undergone significant orbital shifts, reshaping their early solar system environment and influencing the formation of other celestial bodies. Furthermore, Uranus and Neptune pose questions about their internal structures and magnetic fields. Both planets exhibit unusual magnetic fields that are tilted and offset from their rotational axes, unlike the more aligned fields of Earth, Jupiter, and Saturn. This anomaly suggests complex internal dynamics, possibly involving convecting layers of ionically conductive fluids rather than a simple metallic hydrogen core. Additionally, Uranus's extreme axial tilt, essentially knocked over on its side, triggers speculation about a colossal impact event in its past, challenging our understanding of planetary collision dynamics. The atmospheric compositions and weather patterns on these distant worlds also captivate scientists. For instance, Neptune boasts the strongest winds in the solar system, despite receiving only a fraction of the sunlight Earth does. The mechanisms driving these ferocious winds and the energy sources fueling such dynamic atmospheres remain elusive. Probing these mysteries involves more than just curiosity. By examining ice giants, we can compare and contrast them with exoplanets of similar sizes and compositions, offering broader insights into planetary systems beyond our own. The study of ice giants like Uranus and Neptune helps unravel the complexities of planetary formation, migration, and internal structure. Each twist and turn in their attributes enriches our broader understanding of the cosmos, suggesting that learning their secrets could illuminate the broader narratives of planetary genesis and evolution, both within our solar system and beyond. The concept of an ocean planet, a celestial body entirely enveloped in water, presents a tantalizing prospect for the potential support of life. Ocean planets provide a unique environment where life could not only survive but possibly thrive, existing in conditions vastly different from those on Earth. These planets could range from having shallow seas to deep, global oceans, some potentially stretching hundreds of kilometers beneath the surface, encompassing the entire surface with water. One of the primary aspects that makes an ocean planet hospitable is the universal solvent nature of water, which facilitates a wide range of chemical reactions necessary for life. Even though the extreme pressures in the deep oceans might seem inhospitable, life forms could still thrive much like the extremophiles found in Earth's deep-sea hydrothermal vents. These Earth analogues derive their energy not from sunlight, but from the chemical-rich, superheated water emitted by the vents. Similarly, an ocean planet might possess geothermal vents along its seabed, providing essential nutrients and energy sources to sustain rich ecosystems of microorganisms, which form the foundational bedrock of more complex life forms. Moreover, ocean planets could maintain stable, internally generated climates thanks to the heat retention and circulation properties of water. The oceans can store immense amounts of heat, buffering drastic temperature swings between day and night or seasonal changes. If the planet has a significant atmosphere enriched with greenhouse gases, it could further moderate temperatures, creating a stable environment conducive to life. Additionally, the potential for a dynamic water cycle involving the evaporation and precipitation of water could encourage nutrient distribution throughout the planet's oceans, enriching the entire water column with essential elements needed for life. The potential for life on an ocean planet isn't confined to the deep sea. In zones closer to the surface, where sunlight can penetrate, photosynthetic organisms could flourish, forming the basis of complex food webs. Such diversity of life, ranging from simple microorganisms to possibly more sophisticated multicellular creatures, would inherently depend on the distribution of light, energy sources, and nutrients. The interplay between light at the surface and geothermal energy at the depths could create banded ecosystems, each with its own unique life forms and evolutionary pathways. Thus, an ocean planet offers an intriguing and plausible venue for extraterrestrial life. By exploring and understanding these potential worlds, we broaden our horizons of what kinds of environments can support life, suggesting that our universe could be teeming with diverse, water-based life forms just waiting to be discovered. Exoplanets residing in the habitable zones of red dwarf stars offer compelling settings for the potential signs of life. Red dwarf stars, or M-dwarfs, are the most common type of stars in our galaxy, making them prime targets in the search for extraterrestrial life. Despite their small size and cooler temperatures compared to stars like our Sun, red dwarfs can support planets that maintain liquid water, a key ingredient for life as we understand it. Identifying potential biosignatures on these exoplanets involves examining a variety of factors, including atmospheric composition, surface conditions, and potential biological processes. One of the most promising signs of life is the detection of specific gases in an exoplanet's atmosphere that could indicate biological activity. For instance, oxygen and ozone are considered strong biosignatures because on Earth they are byproducts of photosynthetic life. However, given the unique conditions around red dwarfs, we must also consider other gases such as methane and nitrous oxide. Methane can be produced through geological processes, but in the right balance with gases like oxygen, it becomes a compelling indicator of biological activity. Similarly, the presence of nitrous oxide, a byproduct of microbial activity on Earth, could be a strong indicator of life if detected on an exoplanet. The behavior and stability of these gases are equally important. Red dwarf stars are known for their stellar flares and variability, which can impact a planet's atmosphere. Persistent or stable levels of potential biosignature gases, despite these challenges, could strongly suggest a biological source replenishing these compounds. Advanced spectrometry from telescopes like the James Webb Space Telescope will play a critical role in examining these atmospheres, looking for such hints of life from light-year distances. Furthermore, the surface conditions and potential ecosystem dynamics on these planets also offer clues. For instance, the relative stability of liquid water bodies, oceans, lakes, or even subsurface reservoirs can provide environments where life could potentially thrive. Tidal forces from the red dwarf could promote geothermal activity, creating niches similar to hydrothermal vents on Earth. Additionally, identifying signs of photosynthesis adapted to the infrared light emitted by red dwarfs could point towards surface life forms uniquely tailored to their star's spectrum. In conclusion, while red dwarf systems present unique challenges, they also offer a wide array of indicators that could point to the presence of life. By meticulously studying atmospheric compositions, surface conditions, and potential biological processes, we edge closer to answering one of humanity's most profound questions. Are we alone in the universe? A planet with a thick hydrogen atmosphere opens up a fascinating frontier for the potential of exotic forms of life, expanding our understanding of what constitutes habitable conditions. Unlike Earth's atmosphere, which is nitrogen and oxygen rich, a hydrogen-dominated atmosphere would present a different set of chemical and physical conditions. Despite its differences, such an environment could theoretically support life forms that thrive on hydrogen-based chemistry rather than oxygen-based metabolism. One crucial aspect to consider is that hydrogen, being a lightweight molecule, is a potent greenhouse gas. This characteristic implies that even a planet far from its star could maintain warm enough temperatures to support liquid water, which is crucial for life as we understand it. Some theoretical models suggest that on such planets, hydrogen could facilitate a stable, warm climate, enabling a wide range of biochemistries to flourish. For example, organisms could potentially use hydrogen to drive metabolic processes, akin to how some bacteria on Earth utilize hydrogen in chemosynthesis. These hypothetical life forms might use hydrogen as a vital chemical energy source, exploiting its abundance much like aerobic organisms on Earth utilize oxygen. Energy sources for life in a hydrogen-rich atmosphere would likely differ from the sun-dependent photosynthetic processes we know. On Earth, certain extremophiles dwell in environments where hydrogen is more prevalent and play a vital role in their ecosystems. One example is methanogens, microorganisms that produce methane by reacting hydrogen with carbon dioxide. Similar types of archaea-like organisms might thrive on an exoplanet with a thick hydrogen atmosphere, converting hydrogen into various biochemical energies to sustain their life processes. Another intriguing possibility is that such an atmosphere might allow for different kinds of complex organic chemistry. The presence of other elements such as carbon, nitrogen, and oxygen might enable the formation of fascinating organic compounds and polymers, potentially leading to life forms with structures and metabolisms vastly different from anything on Earth. These life forms could use hydrogen in ways we can scarcely imagine, possibly resulting in biochemistries that are far more diverse and exotic. Moreover, hydrogen-rich atmospheres could result in different ecosystem dynamics. For example, without the risk of oxidative stress from oxygen, organisms might evolve unique protective mechanisms against other environmental stresses, such as radiation or extreme temperatures, frequently encountered on planets orbiting different types of stars. Community structures could also be unique, possibly featuring hydrogen-based energy cycles and nutrient transfers that sustain a rich, albeit alien, biosphere. In conclusion, a planet with a thick hydrogen atmosphere could support exotic life forms adapted to unique environmental conditions. The study of such planets challenges our Earth-centric views and compels us to broaden our search for life by considering environments radically different from our own, reminding us that life, as an incredible adaptive force, may indeed find a way even in the most unearthly settings. A planet with an extreme axial tilt, tilted significantly more than Earth's modest 23.5 degrees, would experience dramatic and extreme seasonal changes that make its climate and living conditions highly dynamic and challenging. Such a planet's axial tilt, sometimes approaching or even exceeding 90 degrees, would result in one hemisphere facing the star for a prolonged period, while the other lies in complete shadow, before flipping the exposure as the planet orbits around its star. In practical terms, this means that for extended periods of time, one hemisphere would experience a scorching, unrelenting summer with the sun directly overhead, potentially leading to severe heat and increased radiation levels. During this time, temperatures could soar to extremes, creating a desert-like environment, unless moderated by atmospheric conditions or oceanic influences. The continuous sunlight could result in rapid evaporation of surface water, driving intense weather patterns, including massive storms or even hypercane-like hurricanes. Meanwhile, the opposite hemisphere would be plunged into a prolonged, frigid winter with no sunlight at all. Temperatures would plummet, potentially turning the landscape into a frozen wasteland. Glaciers could advance, and if the planet retains bodies of water, they might freeze solid, creating a world draped in ice. Life in these regions would have to adapt to prolonged periods of darkness and cold, potentially entering states of dormancy or utilizing geothermal and other non-solar energy sources to survive. The transition periods between these extremes, what you might call the planet's spring and autumn, would themselves be times of turbulent change. These equinoxes could be characterized by rapid shifts in temperature, massive storms, and possibly flooding as ice from the winter hemisphere melts. The equatorial region of such a planet would likely be the most stable, potentially acting as a haven for life, experiencing a kind of perpetual twilight with more moderate temperatures year-round. For life to thrive on such a planet, it would need to be incredibly adaptable. Flora and fauna might develop unique adaptations such as rapid reproductive cycles to take advantage of the brief but intense periods of favorable conditions during seasonal transitions. Plants might evolve to store energy and water efficiently during prolonged periods of light or darkness, similar to how certain desert plants on Earth store water. Animals might migrate vast distances to follow more stable climates, or they might develop strategies for hibernation or estivation to survive extended periods of inhospitable conditions. Human or intelligent life on such a planet would face enormous engineering challenges, but could also develop unique cultural and technological adaptations to manage the extreme environments. Settlements might be mobile, moving seasonally from one hemisphere to the other, or they might build massive underground or insulated habitats to shield from the extreme cold and heat. A planet with an extreme axial tilt would be a world of stark contrasts and constant change, constantly testing the resilience and adaptability of any life forms that call it home. This variability not only makes for a challenging environment, but also suggests that life, should it exist, would need to be incredibly versatile, capable of enduring and thriving amid some of the most extreme seasonal swings imaginable. Exoplanets with elliptical orbits, also known as eccentric orbits, present significant challenges to our understanding of planetary stability and habitability. Unlike the nearly circular orbits of most planets in our solar system, these exoplanets travel along elongated paths around their stars, leading to drastic variations in their distance from the star throughout their orbit. This eccentricity can have profound effects on the planet's climate, atmospheric dynamics, and overall stability, making them fascinating subjects for study, but also complicating our models of planetary systems. One of the most significant challenges posed by elliptical orbits is the extreme temperature variations that a planet would experience. As the planet moves closer to its star, it encounters intense radiation and heat, potentially leading to scorching temperatures and significant atmospheric expansion. On the other hand, as the planet travels to the farthest point in its orbit, it experiences a dramatic cooling, resulting in possibly freezing conditions. These extreme fluctuations can place considerable stress on any potential atmosphere, potentially stripping it away during close star encounters or leading to freezing and thawing cycles that could impact surface and subsurface chemistry. These temperature swings also make it difficult for stable climates to develop, which are critical for maintaining liquid water, a key ingredient for life as we understand it. The habitable zone around a star, traditionally defined as the region where liquid water can exist, becomes more complex for planets with eccentric orbits. A planet might pass through the habitable zone only during certain parts of its orbit, leading to seasonal-like conditions on a scale much more extreme than anything observed in the solar system. This episodic habitability complicates any prospects for life, as organisms would need to endure highly variable environments with potentially long periods without stable, life-supporting conditions. Moreover, the gravitational interactions resulting from eccentric orbits can impact the planet's rotational dynamics. Tidal forces from the star can cause significant stretching and squeezing of the planet, generating internal friction and heat, a process known as tidal heating. This could potentially create volcanic activity or subsurface oceans, offering niches where life could exist independently of surface conditions. Moons orbiting such planets might also feel these tidal forces, adding another layer of complexity to the dynamical interactions within the planetary system. Complex orbital dynamics further challenge the long-term stability of these systems. The gravitational interplay between planets in a multi-body system can lead to chaotic orbits over astronomical timescales. For example, eccentric orbits might result from past gravitational encounters with other large bodies, suggesting a history of dynamic rearrangements and possible planetary migrations within the system. Despite these challenges, eccentric orbits also offer intriguing possibilities for unique planetary environments unlike any in our solar system. They push the boundaries of our understanding of what conditions could potentially support life and force us to consider a broader array of planetary behaviors and evolutionary paths. Through studying these dynamic systems, scientists gain deeper insights into the resilience and adaptability of potential life forms, the diversity of planetary environments, and the intricate gravitational dances that shape planetary systems across the galaxy. Starburst galaxies are fascinating cosmic phenomena characterized by their extraordinarily high rates of star formation, far exceeding those of typical galaxies like our Milky Way. These galactic bursts of stellar creation can generate thousands of new stars in just a few million years, a blink of an eye in cosmic terms. Understanding how starburst galaxies produce stars at such astonishing rates involves exploring the unique conditions and forces at play within these dynamic systems. At the heart of a starburst galaxy's prolific star formation is an abundance of gas and dust, the raw materials for new stars. These galaxies often contain massive reservoirs of hydrogen gas, which collapse under their own gravity to form dense molecular clouds. Within these clouds, regions become gravitationally unstable and begin to fragment, leading to the birth of new stars. The process is often catalyzed by external events such as galaxy mergers or close encounters with other galaxies. These interactions can compress the gas clouds, triggering a chain reaction of star formation by creating shock waves that further destabilize molecular clouds, making them ripe for collapse. Feedback mechanisms within starburst galaxies also play a critical role. The intense radiation from newly formed stars heats surrounding gas, causing it to expand and compress adjoining clouds, thereby promoting more star formation. Additionally, supernovae, explosions of massive stars, inject energy into the surrounding medium, stirring up gas and dust and causing further regions to collapse and form new stars. This positive feedback loop can sustain high star formation rates for several million years, a period known as a starburst phase. During these phases, starburst galaxies can exhibit brilliant luminosity. The intense ultraviolet light from massive young stars ionizes the surrounding gas, creating regions known as HII regions, which shine brightly in the optical and infrared wavelengths. These galaxies often display complex and chaotic structures, with clumps of young, hot stars interspersed among turbulent gas clouds and dark dust lanes. The rapid rate of star formation in starburst galaxies, however, is not sustainable in the long term. As these galaxies expend their reservoirs of gas and dust, the star formation rate eventually declines. Moreover, the energetic processes within starburst phases can drive powerful galactic winds, expelling gas and dust into intergalactic space and depleting the material available for future star formation. Over time, the starburst phase subsides, and the galaxy continues to evolve, potentially merging with other galaxies. or transitioning into a more quiescent state. Studying starburst galaxies offers valuable insights into the processes of star formation and galaxy evolution. These cosmic laboratories enable astronomers to observe the extremes of star creation and understand the conditions under which massive bursts of star formation can occur. This understanding not only sheds light on the life cycles of galaxies, but also on the broader mechanisms that govern the evolution of the universe. Active galactic nuclei, AGN, play a profound and multifaceted role in shaping their host galaxies, influencing everything from star formation processes to the overall galactic structure. An AGN is a small region at the center of a galaxy that emits an extraordinary amount of energy, primarily due to the accretion of matter onto a supermassive black hole. As matter spirals inward toward the black hole, it forms an accretion disk, heating up and radiating across the electromagnetic spectrum. This intense energy output can have far-reaching effects on the host galaxy. One of the most significant influences of an AGN is through the process known as AGN feedback, which can either suppress or enhance star formation within the galaxy. In its more classical form, AGN feedback is often negative, meaning that the intense radiation and energetic outflows from the AGN can heat up or expel the gas within the galaxy, making it difficult for the gas to cool and condense into new stars. These powerful outflows, jets and winds can drive huge amounts of gas out of the galaxy's central regions, effectively quenching star formation. This process can lead to the cessation of star formation in the entire galaxy, transforming it from a star-forming, often spiral galaxy into a more quiescent, elliptical galaxy over time. On the flip side, there are scenarios where AGN activity can potentially enhance star formation. The outflows and jets from the AGN can compress gas clouds as they plow through the interstellar medium, triggering the collapse of these clouds into stars. This is a more localized effect, and tends to happen in regions where the AGN-induced pressure is just right to prompt cloud collapse without dispersing the gas completely. This dual nature of AGN feedback illustrates the complex interplay between the central black hole and its host galaxy. AGN also have a profound impact on the larger-scale structure of their host galaxies and beyond. The energy released by an AGN can help regulate the growth of the host galaxy by controlling the availability of star-forming material. This regulatory effect can extend to the galactic halo, influencing the temperature and density of gas within the galaxy's gravitational influence. Additionally, AGN can affect the intergalactic medium, enriching it with heavy elements through the expulsion of gas and dust, thereby influencing the evolution of neighboring galaxies and the broader cosmic environment. Observationally, active galactic nuclei contribute to the distinct properties seen in various galaxy types. Seyfert galaxies, quasars, and blazars are all examples of galaxies with active nuclei, each providing unique insights into the life cycle and characteristics of AGN. Understanding AGN also helps astronomers gain insights into the early universe, since some of the most luminous known AGN quasars are observable at great distances, acting as beacons from the past and offering clues about the conditions and processes in the early stages of galaxy formation and development. AGN significantly influence their host galaxies via complex feedback mechanisms that can both inhibit and stimulate star formation, alter galactic structures, and affect the interstellar and intergalactic media. These multifaceted interactions highlight the central role of supermassive black holes in galaxy evolution, making AGN not just fascinating phenomena, but also key components in our broader understanding of the cosmos. Ultra-diffuse galaxies, UDGs, are one of the most intriguing and enigmatic objects in the cosmos, challenging our conventional understanding of galaxy formation and composition. These galaxies are puzzling because, even though they are as large as the Milky Way, they possess incredibly few stars, making them appear ghostly and faint. What makes UDGs particularly fascinating and mysterious is their high dark matter content. They seem to be dominated by dark matter, which comprises the bulk of their mass despite their sparse stellar populations. One of the primary mysteries surrounding UDGs is their formation process. Traditional galaxy formation theories suggest that galaxies form through the accretion of gas and subsequent star formation, regulated by the gravitational influence of dark matter halos. However, UDGs defy this model by displaying very little star formation. Several hypotheses have been proposed to explain their existence. One theory posits that they are failed galaxies. They have massive dark matter halos which, for some reason, could not efficiently convert gas into stars. This inefficiency might be due to early feedback processes such as supernova winds or active galactic nuclei expelling gas before it could form stars. Alternatively, UDGs might be tidal remnants, formed through the interactions and stripping of more conventional galaxies by larger neighboring galaxies or galaxy clusters. The role of dark matter in UDGs is another profound mystery. Observations indicate that UDGs are exceptionally dark matter-rich, which raises questions about the nature and distribution of dark matter within these galaxies. This extensive dark matter can offer clues about dark matter properties and behavior on cosmic scales. Some UDGs, like those identified in the Coma cluster, appear to have dark matter halos comparable in mass to those of much larger galaxies, yet they scarcely contain stars. This implies that dark matter played a fundamental role in their evolution, but the exact mechanisms by which dark matter affects their development are still not fully understood. Interestingly, the discovery of UDGs challenges current cosmological models and simulations. Standard models of cosmology predict a certain distribution and behavior of galaxies based on the understanding of dark matter and baryonic matter interactions. UDGs, with their unusual properties, force astronomers to reconsider these models and explore new ones that can account for such anomalies. For instance, some theories suggest that UDGs could form in dark matter halos with specific properties that are yet to be fully characterized, implicating new facets of dark matter physics. Furthermore, the presence of UDGs in various environments, from dense clusters like Coma to more isolated regions, adds to the complexity. In galaxy clusters, UDGs might be the remnants of tidal interactions, but in isolation, different formation processes might be at play. Comparative studies of UDGs in different environments are essential to untangle the various factors contributing to their unique characteristics. Finally, the composition and stability of UDGs are also points of intrigue. The structural integrity of such diffuse systems with minimal stellar mass yet significant dark matter presence raises questions about their internal dynamics and long-term stability. How these galaxies maintain their structure and resist tidal disruption remains a compelling field of study. Ultra-diffuse galaxies present a conundrum that challenges our understanding of galaxy formation, the role of dark matter, and the behavior of cosmic structures. They serve as natural laboratories for studying the interaction of baryonic matter and dark matter, and their mystery drives astronomers to refine existing models and develop new theories that can better explain such extraordinary and ghostly galaxy formations. Ring galaxies are among the most striking and visually captivating structures in the cosmos, characterized by a bright ring of stars and other material surrounding a typically less luminous core. Their formation is primarily attributed to galactic collisions and interactions, offering valuable insights into the dynamics of these colossal cosmic events and the subsequent evolution of galaxies. The most widely accepted theory for the formation of ring galaxies involves a bullseye collision, where a smaller intruder galaxy passes directly through the center of a larger disk galaxy. This collision sends a powerful shockwave outward through the disk of the larger galaxy. As this wave travels, it compresses gas and dust, triggering a burst of star formation that manifests as a bright ring. The gravitational interactions during such an encounter can be extreme, causing material to be radially displaced and restructured into the ring shape we observe. One of the classic examples of a ring galaxy is the Cartwheel Galaxy, located about 500 million light-years away in the constellation Sculptor. Observing such a galaxy provides astronomers with a natural laboratory to study the effects of gravitational forces and shockwave-induced star formation. The ring in these galaxies is typically rich with young hot stars, indicative of recent and intense star-forming activities. This is contrasted with the older stars and less pronounced star formation in the core, which may have been disrupted by the collision. Ring galaxies tell us a great deal about the mechanics and outcomes of galactic collisions. First, they illustrate how galactic interactions can dramatically reshape galaxies and lead to the formation of new structures. The fact that relatively few ring galaxies exist compared to other types of galaxies indicates that perfect bullseye collisions are relatively rare events. However, when they do occur, they offer a clear demonstration of the conservation of angular momentum and the propagation of density waves through a galactic disk. Moreover, studying ring galaxies helps astronomers understand the distribution and behavior of interstellar medium, ISM, within galaxies. The propagation of the collision-induced shockwave reveals the gas density and the conditions required for star formation. By examining the luminosity, color, and distribution of stars within the ring, researchers can infer the age of the starburst and therefore determine when the collision occurred. This in turn aids in creating a timeline for the dynamic interactions and evolutionary processes of the galaxies involved. Additionally, the investigation of ring galaxies and their formation contributes to our broader understanding of galaxy formation and evolution. It underscores the importance of minor mergers, collisions between galaxies of vastly different sizes, in shaping the structure and star formation rates of galaxies in the universe. These interactions are not just disruptive, they can also rejuvenate galaxies by supplying fresh gas that fuels new rounds of star formation. Ring galaxies are the spectacular outcomes of galactic collisions, specifically head-on collisions that send shockwaves through a galaxy's disk. They provide critical insights into the dynamics of galactic interactions, the distribution and behavior of interstellar matter, and the star formation processes triggered by such events. Studying ring galaxies helps astronomers piece together the complex narrative of galaxy life cycles, enriching our understanding of the universe's grand tapestry. Dark galaxies are a tantalizing discovery in the realm of cosmology, offering a window into the unseen portion of our universe. These elusive entities, composed almost entirely of dark matter, lack the bright, blazing stars that make typical galaxies visible. Without stars to light them up, dark galaxies evade direct observation, revealing their presence only through gravitational effects on nearby visible matter, or through minute distortions in the cosmic microwave background radiation. Imagine, if you will, entire galaxies, vast in size, silently coasting through the cosmos, undetectable to our telescopes, but intricately interwoven into the structure of the universe. The implications of such dark galaxies are profound. For one, they strengthen our understanding of dark matter, which makes up about 27% of the universe. This mysterious substance, 5 times more prevalent than ordinary matter, exerts gravitational force, yet emits no light. Finding dark galaxies filled solely with dark matter suggests that this invisible hand plays a more complex and significant role in galactic formation and evolution than previously thought. Furthermore, these dark entities might serve as cosmic laboratories, allowing scientists to study the properties of dark matter in isolation from the baryonic matter that usually accompanies galaxies. This could potentially uncover new physics beyond the standard model, altering our comprehension of the universe's fundamental building blocks. So, while these hidden giants remain enigmas, their discovery propels us into a deeper investigation of the cosmic puzzle that is dark matter. Galaxy clusters are among the most massive structures in the universe, binding together hundreds to thousands of galaxies through their immense gravitational pull. These cosmic colossi paint a vivid picture of the large-scale structure of the cosmos, acting as beacons that illuminate the intricate framework known as the cosmic web. Imagine looking out into space and seeing galaxies not as isolated islands, but as parts of vast networks interconnected by filaments of dark matter and gas. This web-like structure stretches across billions of light-years, with galaxy clusters forming the bright glowing nodes where these filaments intersect. These clusters reveal the universe's underlying structure through a variety of observational techniques. One key method is gravitational lensing, where the mass of a galaxy cluster bends and magnifies light from objects lying behind it. This not only maps the distribution of visible matter, but also traces the dark matter that makes up most of the cluster's mass. Additionally, X-ray observations of the hot gas within clusters, which can reach temperatures of tens of millions of degrees, provide further insights. The emitting X-rays highlight the intracluster medium and reveal the dynamic processes, such as collisions and mergers, that shape these colossal assemblies. By studying the spatial distribution and evolution of galaxy clusters, cosmologists can infer the properties of dark matter and dark energy, the latter of which drives the accelerated expansion of the universe. Thus, galaxy clusters serve as both signposts and laboratories, enhancing our understanding of the universe's grand architecture and its underlying physical laws. Gravitational lensing acts like a cosmic magnifying glass, enabling astronomers to peer deeper into the distribution of dark matter within galaxies. When a massive object, such as a galaxy or galaxy cluster, lies between a distant light source and the observer, its gravitational pull bends and focuses the light from the source. This results in various observable phenomena, such as multiple images of a single distant galaxy, arcs, or even rings of light, known as Einstein rings. By meticulously analyzing these distortions, scientists can map the presence and concentration of dark matter, which remains otherwise invisible. The distribution of dark matter revealed through gravitational lensing offers critical insights. For one, it shows that dark matter does not spread uniformly across the galaxy. Instead, it tends to clump together, creating dense cores and extended halos around visible matter. This clumping pattern corroborates current cosmological models and simulations that suggest dark matter's role in driving galaxy formation and structure. Detailed lensing studies have revealed that many galaxies have much more dark matter than visible matter, by as much as 10-to-1, outlining extensive halos of dark matter that far exceed the luminous parts of galaxies. Additionally, gravitational lensing helps in probing substructures within dark matter halos, which standard observational methods can't detect. These small-scale features can offer clues about the nature of dark matter particles and their interactions. Through these sophisticated cosmic-scale experiments, gravitational lensing not only unlocks the hidden architecture of dark matter, but also refines our models of how galaxies, and indeed the universe itself, have evolved over billions of years. Dwarf galaxies, though diminutive in size compared to their colossal counterparts, play a significant role in the evolution of larger galaxies, often acting as cosmic building blocks. These smaller galaxies are abundant in the universe and frequently serve as the primary reservoirs of dark matter and gas. Through a process known as hierarchical merging, dwarf galaxies collide and amalgamate with larger galaxies, contributing stars, gas, and dark matter. This ongoing merger process shapes the structure and evolution of larger galaxies, such as our own Milky Way. When dwarf galaxies are assimilated, they can trigger bursts of star formation in the host galaxy by funneling in fresh gas. This can rejuvenate older stellar populations and lead to the formation of new star clusters and even new spiral arms. Moreover, these interactions can induce dynamic changes in the structure and morphology of the host galaxy, influencing properties such as its disk thickness, bar formation, and spiral structure. The stellar streams and tidal tails resulting from these mergers provide observable evidence of such interactions and serve as fingerprints of these cosmic cannibalistic events. Additionally, examining the chemical composition of stars contributed by dwarf galaxies helps astronomers understand the chemical evolution and enrichment history of larger galaxies, shedding light on how elements essential for life were dispersed through the cosmos. The ongoing discovery and study of dwarf galaxies around the Milky Way, including enigmatic entities like the Sagittarius dwarf elliptical galaxy and the Large Magellanic Cloud, highlight the lasting impact these small galaxies have on the grander tapestry of galactic evolution. By slowly but surely building up mass, triggering star formation, and altering the dynamics of their larger neighbors, dwarf galaxies underscore the intricate interplay between cosmic structures across different scales. The intergalactic medium, IGM, and the cosmic web play crucial roles in shaping the structure and dynamics of the universe. The IGM, a vast and tenuous sea of gas primarily composed of hydrogen and helium, fills the space between galaxies and serves as the reservoir from which galaxies draw material. This medium is not evenly distributed. Instead, it aligns itself along the filaments, sheets, and voids that form the cosmic web, a network-like structure that extends across the entire universe. The cosmic web's filaments are the highways along which matter flows, guided by the gravitational pull of dark matter. Galaxies are often found where these filaments intersect, forming galaxy clusters at the nodes. The IgM within these filaments can become heated to millions of degrees, emitting X-rays as it funnels into galaxies and galaxy clusters. This process of accretion is fundamental to galaxy growth and evolution, as it supplies the necessary gas for star formation and black hole feeding. The interaction between the IgM and galaxies within the cosmic web also affects the chemical enrichment of the universe. As galaxies form stars, they expel enriched gases back into the IgM through supernova explosions and stellar winds, disseminating heavier elements like carbon, oxygen, and iron. These processes play a critical role in the chemical evolution of the universe and the formation of new stars and planets. Additionally, observations of the IgM through quasar absorption lines, where distant quasars' light is filtered through the medium, provide valuable insights into the distribution and state of matter in the early universe. Thus, the IgM and cosmic web are not just passive components, but active participants in the cosmic story, orchestrating the flow of matter and energy, fostering the growth and evolution of galaxies, and enriching the universe with the building blocks of stars and life. Galactic halos present a complex puzzle that challenges and refines our understanding of galaxy formation and evolution. These spherical regions of dark matter surround galaxies, extending far beyond the visible stellar components. Unlike the concentrated disks and bulges of galaxies, halos are diffuse yet massive, often containing a significant portion of a galaxy's total mass. One of the primary challenges posed by galactic halos is their largely invisible nature, as they do not emit light but exert gravitational influence, making them detectable primarily through their effects on the rotation curves of galaxies and gravitational lensing. The presence of these dark matter halos implies that our models of galaxy formation must account for this unseen mass. Traditional models, considering only visible matter, failed to explain why galaxies rotate in a manner inconsistent with their luminous mass distribution. Dark matter halos provide the missing piece of this puzzle, explaining why the outer regions of galaxies rotate faster than expected. However, the precise nature of dark matter remains one of the most significant mysteries in cosmology. Various candidates, such as weakly interacting massive particles, WIMPs and axions, have been proposed, but none have been directly detected, leaving a gap in our comprehensive understanding. Galactic halos also challenge our understanding of how galaxies evolve. The interactions between dark matter and baryonic matter within these halos influence processes ranging from star formation to galactic mergers. For instance, the stable, enduring nature of dark matter halos could offer a scaffold upon which gas can cool and condense to form new stars, governing the life cycle of a galaxy over billions of years. Additionally, the structure and substructure of halos, including the presence of subhalos, smaller concentrations of dark matter within the larger halo, impact the dynamics and eventual fate of satellite galaxies. By studying these halos, we can gain insights into the hierarchical nature of galaxy assembly and the role of dark matter in shaping the universe. Thus, while galactic halos challenge our current models, they also provide an essential framework for understanding the cosmic web and the intricate dance of galaxies within it. The Great Attractor is one of the most enigmatic features in our cosmic neighborhood, exerting a gravitational pull so immense that it influences the motion of entire clusters of galaxies, including our own Milky Way. Located roughly 150 to 200 million light-years away in the direction of the constellation Centaurus, this massive region contains a gravitational anomaly that significantly affects the flow of galaxies within a few hundred million light-years. However, its exact nature remains shrouded in mystery due to its position behind the dense plane of the Milky Way, which obscures our view, a region the astronomers refer to as the zone of avoidance. Several hypotheses attempt to explain the Great Attractor. One prevailing theory suggests that it is a supercluster or a complex of superclusters, aggregating vast amounts of mass, including both visible galaxies and a significant amount of dark matter. Observations indicate that this area is rich in galaxy clusters, such as the Norma cluster, which contribute to its overwhelming gravitational pull. The dark matter component, as with other large-scale structures in the universe, plays a crucial role in creating this gravitational influence. The Laniakea supercluster, which includes our Milky Way, is thought to be part of the larger structure funneling toward the Great Attractor, illustrating the interconnected nature of cosmic flows and gravitational dynamics. Another layer of complexity has been added by observations suggesting there might be even larger structures beyond the Great Attractor, such as the Shapley supercluster, which lies about 650 million light-years away. This suggests that what we perceive as the Great Attractor might just be an intermediate gravitational feature within a network of even grander cosmic entities. Understanding the Great Attractor opens up inquiries into the distribution of mass in the universe and the role of dark energy in cosmic expansion. As astronomers develop more advanced tools for peering through the cosmic veil, the true nature of the Great Attractor will likely come into sharper focus, providing a deeper understanding of the invisible forces sculpting our universe. The WOW signal represents one of the most intriguing and enduring mysteries in the search for extraterrestrial intelligence, SETI. Detected on August 15, 1977, by Dr. Jerry Amon using the Big Ear radio telescope at Ohio State University, this narrowband radio signal stood out due to its unusual intensity and frequency. Lasting 72 seconds, the signal bore the hallmarks of a potential extraterrestrial transmission, prompting Amon to jot "WOW" in the margins of the data printout, a label that has endured ever since. Although attempts to locate the signal again have been unsuccessful, its peculiar characteristics raise profound questions about the existence and nature of intelligent life beyond Earth. The WOW signal challenges our understanding in several ways. Firstly, its narrowband nature is precisely what SETI researchers expect from an artificial source, as natural cosmic phenomena typically produce broadband noise. If the signal did indeed originate from an intelligent civilization, it signifies that they possess technology capable of transmitting focused, powerful radio waves across interstellar distances. This would imply an advanced level of technological sophistication far beyond our current capabilities. The challenge lies in the fact that, without repetition, it's impossible to decode or interpret the signal definitively, leaving scientists in a state of tantalizing ambiguity. Moreover, this unexplained signal, along with other similar anomalies, such as the recent discovery of fast radio bursts, FRBs, sparks debates about our methods and assumptions in the search for extraterrestrial intelligence. While most FRBs are believed to have natural astrophysical origins, their initial discovery prompted some speculation about artificial sources. These transient events challenge the SETI community to refine their detection strategies, balancing the rigorous search for natural explanations with the openness to extraordinary ones. They push us to ask whether our technological and observational limitations might prevent us from identifying or understanding potential extraterrestrial communications. As our tools improve and our search broadens, these enigmatic signals continue to stir our imagination and drive our quest to answer one of humanity's most profound questions: are we alone in the universe? Tabby's star, formerly known as KIC 8462852, has captured the imagination of both the scientific community and the public due to its highly irregular and perplexing dimming patterns. Discovered by the Kepler Space Telescope and brought to prominence by astronomer Tabitha "Tabby" Boyajian, from whom it gets its nickname, this star exhibits drops in brightness of up to 22%, which is far more substantial than what is typically observed from exoplanets transiting their host stars. Unlike the predictable and regular dips caused by orbiting planets, the dimming of Tabby's star appears erratic and lacks a consistent periodicity, leading to a plethora of hypotheses about its cause. Several natural explanations have been proposed. One leading theory suggests that a large cloud of disintegrating comets or debris from a shattered planet might be periodically passing in front of the star, although this scenario would require an enormous and highly coincidental aggregation of material. Another hypothesis considers the possibility of intrinsic stellar variability, such as changes within the star itself that affect its brightness. Additionally, some astronomers propose the presence of an enormous ringed or oddly shaped exoplanet, although this too faces significant observational and theoretical challenges. The intrigue surrounding Tabby's star has drawn attention to other stars with similar unexplained dimming patterns, such as VVV-WIT 08, an object observed by the Vista variables in the Via Lactea survey. This star also exhibits drastic reductions in brightness, leading scientists to consider a multitude of potential causes, including the possibility of large disk structures or even previously unseen types of stellar companions. Among the more speculative yet enthralling hypotheses is the idea of megastructures built by an advanced extraterrestrial civilization, such as Dyson spheres, vast structures intended to harvest energy from a star. While there is no concrete evidence supporting this idea, it has fueled public interest and emphasizes the importance of keeping an open mind in scientific inquiry. Research into these mysterious stars continues, leveraging data from a variety of telescopes and astronomical surveys. As technology advances, providing higher resolution and more comprehensive observational capabilities, future studies promise to shed light on these cosmic enigmas. Whether these dimming patterns result from natural phenomena or hint at something far more exotic, they serve as a catalyst for exploring and understanding the complexities and wonders of our universe. Cosmic voids and the large-scale structure of the universe present profound challenges and opportunities for cosmology, compelling us to rethink and refine our understanding of the cosmos. These vast, seemingly empty regions of space, known as cosmic voids, span tens to hundreds of millions of light-years and are interspersed among the filamentary structures of the cosmic web, which hosts galaxies and clusters. Void galaxies themselves are sparsely distributed, making these regions less dense compared to their filamentary counterparts. One of the primary challenges posed by cosmic voids is their impact on our understanding of dark matter and dark energy. The distribution and behavior of matter within these voids provide a unique testing ground for cosmological models. Unlike dense regions, which can be dominated by gravitational clustering and interactions, voids are less crowded and thus are more sensitive to the expansion of the universe driven by dark energy. This makes them excellent laboratories for studying the properties and effects of dark energy, as well as for testing alternative theories of gravity. The way galaxies within these voids evolve and interact can reveal subtle forces at play, potentially unveiling new physics beyond the current cosmological paradigm. Cosmic voids also challenge our understanding of how galaxies form and evolve. The galaxies within voids are quite different from those in more crowded environments. They tend to have lower luminosities, lower star formation rates, and unique morphologies. This suggests that environmental factors significantly influence galactic development. By studying void galaxies, astronomers can isolate these environmental effects and better understand the intrinsic processes that drive galaxy formation. Further complications arise when integrating observations of cosmic voids with large-scale simulations of the universe. While our current models, including the Lambda Cold Dark Matter (LCDM) model, successfully reproduce many large-scale features of the universe, discrepancies at smaller scales, such as the distribution and properties of void galaxies, indicate that there might be gaps in our understanding. These discrepancies force cosmologists to refine their simulations, incorporating more complex interactions between dark matter, dark energy, and baryonic matter. The presence of cosmic voids and their distinct properties serve as critical challenges and calibrators for our cosmological models. They provide a deeper, more nuanced understanding of the universe's composition and evolution. As observational techniques improve and more data becomes available, these cosmic voids will continue to stretch the boundaries of our knowledge, potentially leading to revolutionary breakthroughs in cosmology. The Cosmic Microwave Background, CMB. Cold spot is a region in the CMB that exhibits a significantly lower temperature than the surrounding areas. Discovered by the Wilkinson Microwave Anisotropy Probe, WMAP, and confirmed by the Planck satellite, this roughly 20-degree wide area has puzzled scientists due to its anomalously low temperature, approximately 70 microkelvin colder than the average CMB temperature of around 2.7 Kelvin. The CMB itself is the afterglow of the Big Bang, providing a snapshot of the early universe approximately 380,000 years after its inception. Variations in the temperature and density of the CMB are expected and have been extensively studied to understand the formation of large-scale structures in the universe. However, the CMB cold spot stands out as an anomaly that challenges current cosmological theories. One significant implication of the CMB cold spot is its potential to test and refine the standard model of cosmology. Most conventional explanations attribute the cold spot to a supervoid, a massive, underdense region in the universe, located along our line of sight. Such voids could cause the integrated Sachs-Wolf effect, where photons lose energy while passing through the void, resulting in the observed cold region. However, even this explanation does not completely account for the extreme coldness and size of the spot, leaving room for alternative theories. Among these theories is the tantalizing possibility that the CMB cold spot could be evidence of a parallel universe. Some models of the multiverse hypothesis suggest that our universe is one of many, each potentially with different physical laws and constants. According to this theory, the cold spot might be the result of a collision between our universe and another universe, creating a bruise in the form of this unusually cold region. Although this idea is highly speculative and lacks direct evidence, it spurs intriguing discussions about the nature of reality and the potential existence of other universes. To substantiate or refute these theories, ongoing and future observations are crucial. Detailed studies of the surrounding cosmic structures, analyses of galaxy distributions, and extensive computer simulations are employed to better understand the origin and nature of the CMB cold spot. As our observational capabilities advance, we may get closer to solving this cosmic mystery. Whether it turns out to be a statistical fluke, a result of large-scale cosmic structures, or perhaps a hint of something far more exotic, the CMB cold spot continues to captivate scientists, pushing the boundaries of our understanding of the universe. Fast radio bursts, FRBs, are one of the most confounding phenomena in modern astronomy, capturing the curiosity of scientists worldwide since their discovery in 2007. These incredibly brief but intense bursts of radio waves last only a few milliseconds, but can emit more energy in that time than the sun does in an entire day. Despite numerous detections, the precise origins and mechanisms behind FRBs remain elusive, making them a fascinating enigma for researchers. One of the primary mysteries surrounding FRBs is their unknown source. The diverse theories range from highly magnetic neutron stars known as magnetars to black hole activity, to even more speculative ideas like extraterrestrial civilizations. The characterization of repeating FRBs, those that recur from the same location, adds another layer of complexity. For instance, FRB 121102, a well-known repeater, has shown irregular burst patterns that challenge simple explanations. The fact that some FRBs repeat while others seem to be one-off events suggests that there might be multiple progenitors or mechanisms producing these bursts. Additionally, the distances of these FRBs, often billions of light-years away, imply that whatever produces them must be immensely powerful. The dispersion measure of FRBs, which quantifies the amount of interstellar and intergalactic material the signal has traveled through, indicates their extragalactic origins. This vast distance complicates pinpointing their exact locations and understanding the environments in which they originate. Several FRBs have been traced to specific galaxies, and even particular regions within those galaxies, providing some clues but not yet a complete picture. The study of FRBs is evolving rapidly, with new detections occurring frequently thanks to advanced radio telescopes like CHIME in Canada and ASCAP in Australia. These instruments have increased the rate of FRB discoveries and improved our ability to locate their origins more precisely. However, each new detection often raises as many questions as it answers, underlining the complexity of these cosmic events. FRBs remain one of the biggest mysteries in astronomy due to their enigmatic origins, enormous energy, and rapid, transient nature. They challenge our understanding of the universe's most extreme environments and astrophysical processes. As observational techniques improve and more data become available, scientists are hopeful that the key to unraveling the mystery of FRBs may soon be within reach, potentially opening the door to new realms of astrophysical knowledge. Ultra-high-energy cosmic rays, UHCRs, which are charged particles with energies exceeding 10 circumflex 18 electron volts, are among the most enigmatic and energetic phenomena in the universe. Their extreme energies are millions of times greater than those produced in human-made particle accelerators, prompting many questions about their origin. Despite decades of research, the precise sources of these cosmic rays remain largely speculative, although several compelling theories and potential astrophysical candidates have been proposed. One leading hypothesis suggests that UHCRs originate from extragalactic sources, such as active galactic nuclei, AGNs. AGNs are supermassive black holes at the centers of galaxies that can generate enormous amounts of energy through the accretion of matter. The jets emitted by AGNs, which can extend for millions of light years, are thought to be capable of accelerating particles to ultra-high energies. These jets interact with magnetic fields and ambient material, creating shock waves that can propel particles to astonishing speeds. Another strong candidate for the source of UHCRs is gamma-ray bursts, GRBs. GRBs are extremely energetic explosions observed in distant galaxies, typically associated with the collapse of massive stars or the merger of neutron stars. The relativistic jets produced during these cataclysmic events could offer the extreme conditions necessary to boost particles to ultra-high energies. However, the sporadic and transient nature of GRBs poses challenges for directly linking them to UHCRs. Additionally, some theories involve magnetars, which are neutron stars with exceptionally strong magnetic fields. These objects can emit intense energy bursts and could hypothetically accelerate cosmic rays to ultra-high energies through mechanisms involving magnetic reconnection and relativistic shocks. Interestingly, the cosmic rays' isotropic distribution on the sky, meaning they arrive equally from all directions, supports the idea of extragalactic origins. Should UHCRs primarily originate from within our galaxy, we would expect a more anisotropic distribution due to the Milky Way's structure. Recent observations have shown some degree of anisotropy, hinting that specific extragalactic sources might contribute significantly, but this requires further evidence. Another intriguing element involves the so-called GZK cutoff, named after Grayson, Zatsepin, and Kuzmin. This theoretical limit suggests that cosmic rays with energies above approximately 6x10 circumflex 19 electron volts would interact with cosmic microwave background photons, losing energy over long distances. Yet, cosmic rays observed with energies beyond this limit challenge our understanding and hint at nearby or particularly powerful sources. The sources of ultra-high energy cosmic rays remain one of the significant mysteries in astrophysics. Whether they come from AGNs, GRBs, magnetars, or an altogether different class of astrophysical objects, solving this puzzle will require combined efforts of ground-based observatories like the Pierre Auger Observatory and space-based detectors. As we decode the origins of UHCRs, it could reveal not only the nature of these extraordinary particles, but also provide insights into the most violent and energetic processes in the universe. Gravitational waves have revolutionized our understanding of the universe by opening an entirely new observational window into cosmic events. Predicted by Albert Einstein's general theory of relativity in 1916, these ripples in spacetime are generated by massive celestial objects accelerating, such as binary black hole mergers, neutron-star collisions, or even supernova. The direct detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, marked a milestone, providing a novel way to study astrophysical phenomena that are otherwise invisible to conventional electromagnetic telescopes. Gravitational waves offer several unique advantages in tracing cosmic events. For one, they provide an unaltered view of violent cosmic occurrences. Unlike light, which can be absorbed, scattered, or altered by dust and gas, gravitational waves pass through matter virtually unimpeded. This allows astronomers to observe events like black hole mergers that do not emit any electromagnetic radiation and are thus invisible to traditional optical telescopes. By examining the frequency, amplitude, and polarization of gravitational waves, scientists can infer numerous properties about their sources, including the masses, spins, and orbital dynamics of the merging objects. Additionally, the detection of gravitational waves from neutron-star collisions has ushered in a new era of multi-messenger astronomy, where gravitational wave data is combined with electromagnetic observations. The first such event, detected in August 2017, GW 170817, involved a neutron-star merger that was also observed across the electromagnetic spectrum, from gamma rays to radio waves. This comprehensive observation provided invaluable insights into the formation of heavy elements like gold and platinum, produced by rapid neutron capture in the aftermath of the merger, an answer to a long-standing question in nucleosynthesis. Gravitational waves also enhance our understanding of the universe's fundamental properties. By observing how gravitational waves travel through space-time, scientists can test the predictions of general relativity in extreme conditions, potentially uncovering new physics. For example, any deviations in the speed of gravitational waves from the speed of light might hint at new, unifying theories of gravity. Moreover, these waves can offer clues about the nature of dark matter and dark energy, which remain some of the most profound mysteries in cosmology. Future space-based detectors like the Laser Interferometer Space Antenna, LISA, will further expand our gravitational wave observatory network, allowing detection of lower frequency waves from supermassive black hole mergers and possibly even tracing back to the primordial gravitational waves from the Big Bang. Gravitational waves provide a transformative new method to probe the cosmos, complementing traditional electromagnetic observations. They allow us to witness and study some of the most energetic and enigmatic events in the universe, test the limits of our understanding of fundamental physics, and significantly enhance our grasp of the cosmos. As this relatively young field evolves, it promises to deliver even more profound insights into the workings of the universe. The epoch known as the Cosmic Dawn refers to the period in the universe's history when the first stars and galaxies began to form and shine, heralding the end of the cosmic dark ages. This was a transformative era, occurring roughly 100 to 400 million years after the Big Bang, and it holds myriad mysteries waiting to be unraveled. The first stars, known as Population 3 stars, were composed almost entirely of hydrogen and helium, the primordial elements created during the Big Bang nucleosynthesis, given the absence of heavier elements or metals that were formed later in the universe's evolution. Understanding these stars can offer profound insights into the birth and evolution of cosmic structures, influencing our broader comprehension of the universe's earliest stages. One of the biggest mysteries of the Cosmic Dawn is the role that Population 3 stars played in ionizing the universe. During the Dark Ages, the universe was filled with neutral hydrogen, rendering it opaque to light. The first luminous sources provided the energy needed to ionize this hydrogen, transforming the cosmic environment from neutral to ionized, and thereby making it transparent to light once more. Detecting and studying this epoch of reionization can answer crucial questions about the timing, structure, and sources of ionizing radiation. Did these first stars alone drive reionization, or did dwarf galaxies and the first black holes contribute significantly as well? Another enigma lies in the nature and characteristics of Population 3 stars themselves. These stars, with masses potentially hundreds of times that of the Sun, are thought to have lived short, tumultuous lives, ending in supernovae or even more exotic events like pair instability supernovae. Such events would have dramatically influenced their surroundings, dispersing heavy elements and affecting subsequent star formation and galaxy evolution. Observations of the chemical composition of ancient stars in the Milky Way's halo, which might contain remnants of Population 3 supernovae, can provide indirect evidence of these first stars. The Cosmic Dawn also holds clues regarding the formation of the first black holes and their growth into supermassive black holes found at the centers of galaxies today. The mechanisms through which these initial black holes formed, from the direct collapse of massive stars or other processes, and their subsequent merging and accretion history, are pivotal to understanding galaxy formation and evolution. Future observations and technologies are critical to solving these mysteries. The James Webb Space Telescope, JWST, scheduled to provide unprecedented views of the early universe, aims to capture light from the first galaxies and stars, offering direct observations of the cosmic dawn. In addition, next-generation radio telescopes like the Square Kilometre Array, SKA, seek to map the distribution of neutral hydrogen in the early universe, directly tracing the reionization process. The cosmic dawn and the first stars hold key insights into the early universe's conditions, the processes that governed the formation and evolution of the first cosmic structures, and the subsequent transformation of the universe. Unlocking these secrets promises to enhance our understanding of cosmology, just as the first light brightened the nascent universe. Dark energy, the mysterious force driving the accelerated expansion of our universe, remains one of the biggest enigmas in the world of cosmology. Discovered in the late 1990s through observations of distant supernovae, dark energy is not something we can see or touch. It makes up approximately 70% of the total energy content of the universe, yet its nature eludes us. Scientists have proposed that it might be a property of space itself, prompting every corner of the cosmos to pull away from every other at an ever-increasing rate. Imagine the universe as a loaf of raisin bread rising in an oven. The dough represents space, and as it expands, the raisins, galaxies, move away from each other. However, while bread eventually stops rising, our universe's expansion is accelerating, as if driven by an invisible hand. The exact cause and characteristics of dark energy are still not well understood. Some cosmologists hypothesize it might be related to the cosmological constant, a term Albert Einstein introduced and later discarded, representing a constant energy density filling space uniformly. However, others suggest that dark energy could be a dynamic, changing field, sometimes called quintessence. Instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope provide data, but even with these advanced tools, the true identity of dark energy continues to evade us. This mystery sits at the very bedrock of our understanding of the universe, challenging established notions of physics and spurring the development of new theories to explain how our cosmos ticks. The Drake equation, formulated by Dr. Frank Drake in 1961, serves as a framework to estimate the number of advanced civilizations in our galaxy capable of communication. By incorporating various factors, this equation shines a light on the probabilities and uncertainties of extraterrestrial life. It considers the rate of star formation, the fraction of those stars with planetary systems, the number of planets that could potentially support life, the fraction of planets that develop life, the evolution of intelligent beings, and the likelihood that these civilizations develop technology that emits detectable signals. When multiplied together, these factors yield an estimate of the number of civilizations with whom we might communicate. However, the implications of the Drake equation extend beyond the mere numbers. It highlights the vastness and diversity of our galaxy, suggesting that even a conservative estimate could mean that thousands, if not millions, of civilizations might exist. This has profound implications for our understanding of life in the universe, suggesting that humanity is not unique or alone. Still, many of the equation's terms are based on conjecture due to our current limited astronomical data. This added layer of uncertainty spurs scientific inquiry and technological advancements, encouraging astronomers, biologists, and other scientists to collaborate in the search for extraterrestrial intelligence. By pushing the boundaries of knowledge, the Drake equation reminds us of our endless curiosity and the potential for discovering extraordinary connections beyond our cosmic neighborhood. The quest to detect biosignatures in exoplanet atmospheres is making remarkable strides thanks to advancements in technology and observational techniques. Biosignatures are chemical indicators of life, such as oxygen, methane, or other organic molecules, which could potentially reveal the presence of living organisms. The launch of powerful telescopes like the James Webb Space Telescope, JWST, has been pivotal in this pursuit. With its advanced spectroscopic capabilities, JWST can analyze the light from distant stars filtered through the atmospheres of their orbiting exoplanets. This process, known as transit spectroscopy, allows scientists to identify the specific wavelengths absorbed by atmospheric molecules, effectively revealing their chemical composition. Complementary efforts are underway with ground-based observatories like the European Southern Observatory's Extremely Large Telescope, ELT, which will provide even more detailed observations. These instruments help scientists to refine their models of what an exoplanet's atmosphere might look like if it harbors life. They search for combinations of gases that would unlikely coexist without biological processes, such as the simultaneous presence of oxygen and methane. Earth remains our best reference point, where life significantly alters the atmosphere in detectable ways. As our observational techniques become more precise, the hope is that we will eventually find a living planet, signaling that we are not alone. Advances in this field not only deepen our understanding of life's potential spread across the universe, but also fuel our imagination about the diverse forms that life might take. Discovering microbial life within our own solar system, whether on Mars or the icy moons like Europa, would be a groundbreaking revelation with profound consequences for science, philosophy, and society as a whole. Scientifically, it would provide the first direct evidence that life can arise independently in different environments, bolstering the hypothesis that life may be common throughout the universe. This discovery would prompt a re-evaluation of our understanding of biology, particularly the conditions required for life, and could lead to new branches of research in astrobiology, biochemistry, and planetary science. Mars, with its intriguing seasonal methane emissions, and Europa, with its vast subsurface ocean, are prime candidates for ongoing and future missions designed to detect signs of life. The philosophical and societal implications are equally immense. Finding microbial life close to home would challenge our perceptions of humanity's place in the universe. It would suggest that life isn't a unique Earth phenomenon, but a cosmic inevitability, thereby shifting our anthropocentric worldview. Religions, cultures, and ethical frameworks would all have to grapple with the meaning of this discovery. There would also be practical considerations, such as the ethical treatment of alien microbes, the need to prevent contamination of both Earth and extraterrestrial ecosystems, and potential biosecurity risks. Moreover, it would ignite public imagination and interest in space exploration, potentially leading to increased funding and international cooperation in the pursuit of deeper cosmic understanding. The discovery of microbial life in our solar system would not only answer one of humanity's oldest questions, but also open new chapters of inquiry and reflection about life in the cosmos. Theories of panspermia propose that life can be distributed across the universe through natural mechanisms, suggesting that life did not necessarily originate independently on Earth, but could have been seeded here from elsewhere. The central idea behind panspermia is that microscopic life forms like bacteria or spores can survive the harsh conditions of space travel and potentially colonize new environments when they land. This concept gained traction through the study of extremophiles, organisms on Earth that thrive in extreme conditions like high radiation, vacuum, or intense heat, similar to what would be encountered during interplanetary journeys. There are several ways panspermia could occur. One hypothesis is lithopanspermia, which suggests that life could hitch a ride on meteoroids, asteroids, or comets. For instance, an asteroid impact on a life-bearing planet could eject rock fragments into space, some of which might eventually fall onto another planet, potentially bringing life with them. Another proposed mechanism is radiopanspermia, where microorganisms could be propelled through space by radiation pressure from stars. Directed panspermia, a more speculative idea, suggests that advanced civilizations might intentionally spread life to other planets. Each of these mechanisms underscores the resilience of life's simpler forms and raises the tantalizing possibility that life on Earth or other planets could share a common origin, having traveled immense cosmic distances. If panspermia is indeed a viable method for life distribution, it would imply a greater interconnectedness of life across the universe. This could revolutionize our approach to searching for extraterrestrial life, focusing not just on planets within habitable zones, but also on interstellar objects and moons that might harbor or transport life. Such a perspective enriches our understanding of the cosmic tapestry and enhances our appreciation for the myriad ways life could spread and evolve across the stars. The search for intelligent extraterrestrial life focuses on detecting potential signs or signals that indicate the presence of advanced civilizations. One of the primary methods is the search for extraterrestrial intelligence, SETI, which scans the cosmos for radio waves or other electromagnetic signals that could be artificial in origin. These signals could include narrow bandwidth transmissions or patterns that stand out from natural cosmic noise, possibly indicating deliberate attempts at communication. Our own Earth has been emitting radio waves for over a century, and these signals travel through space, suggesting that other intelligent civilizations might do the same. Another potential sign of intelligent life is the detection of techno-signatures, evidence of advanced technology. This could encompass a variety of phenomena such as laser pulses, artificial light emissions from distant cities, or signs of large-scale engineering projects like Dyson spheres, which are hypothetical megastructures that could encircle a star to harvest its energy. Observatories like the Allen Telescope Array and future projects such as the Square Kilometre Array aim to detect these faint and distant signals. Additionally, space telescopes search for unusual stellar dimming patterns that might indicate the transit of large artificial structures. Beyond electromagnetic signals, researchers are also looking at atmospheric signatures of pollution that could be produced by industrial processes, such as unusually high levels of certain gases that wouldn't occur naturally. The James Webb Space Telescope and ground-based observatories are being employed to analyze exoplanet atmospheres with this in mind. Furthermore, efforts to decode potential alien artifacts or messages, should they ever be discovered, would also fall under this domain. These multifaceted approaches ensure that we cover various possibilities for how intelligent life might reveal itself. Whether through sophisticated technology, deliberate signals, or unintended signs of their existence, the search for intelligent extraterrestrial life combines the forefront of technology with the innate human drive to answer one of our most profound questions: are we alone in the universe? The Fermi paradox and the Great Filter theory provide compelling frameworks for understanding the apparent silence in our search for extraterrestrial intelligence, despite the seemingly high probability of its existence. The Fermi paradox, named after physicist Enrico Fermi, arises from the contradiction between the high likelihood of numerous advanced civilizations existing in our galaxy and the conspicuous lack of evidence for or contact with any of them. Given the age and vast number of stars in the Milky Way, some of which are billions of years older than our Sun, it seems probable that intelligent life should have emerged and developed advanced technologies capable of interstellar communication or travel. Yet, our telescopes and listening devices capture only the void. One resolution to this paradox is the Great Filter theory, which postulates that a highly improbable and difficult to overcome barrier, referred to as the Great Filter, exists in the evolutionary timeline from simple organisms to advanced civilizations. This filter could occur at any stage, from the initiation of life itself, to the emergence of complex, multicellular organisms, to the development of intelligent beings capable of using technology. If the filter is before the stage where intelligent life emerges, this would mean that the formation of life or complex organisms is exceedingly rare. On the other hand, if the filter lies ahead of us, it could imply that advanced civilizations may be prone to self-destruction through nuclear war, environmental collapse, or other catastrophic events. These ideas underscore the rarity and fragility of advanced civilizations. They serve as guides in our search for extraterrestrial life, urging us to consider various scenarios and warning us of potential perils in our future. Understanding where the Great Filter might lie can also influence how we interpret our role in the cosmos and prioritize our efforts for ensuring our own long-term survival. As we continue exploring the universe, these frameworks remind us to remain vigilant, humble, and hopeful in our quest to find our cosmic companions. The nature and motivations of hypothetical advanced alien civilizations are topics that inspire both scientific curiosity and speculative imagination. Given the vast differences in origins, evolutionary paths, and environments, alien civilizations could vary dramatically in their physical forms, societal structures, and technological advancements. Some scientists suggest that truly advanced civilizations might have reached a post-biological phase, where they have transitioned from organic beings to digital or cybernetic forms, capable of living indefinitely and exploring the universe with far greater efficiency. Their technology would likely be so advanced that it could appear magical to us, capable of feats beyond our current understanding. As for their motivations, these could be driven by a range of factors that reflect their own unique evolutionary history and societal priorities. They might be driven by a quest for knowledge and exploration, much like humanity's endeavor to understand the cosmos. Such civilizations could seek to accumulate data, explore new worlds, and understand the fundamental laws of nature. Alternatively, their motivations could include self-preservation and resource acquisition, expanding their reach to ensure the survival and growth of their species. This might involve harvesting energy from stars, as theorized in concepts like Dyson spheres, or colonizing habitable planets. There is also the possibility that advanced civilizations might be inherently peaceful and value cooperation. They may recognize the benefits of mutual assistance and avoid conflicts that could threaten their existence. Conversely, they could be indifferent to other life forms, focusing inwardly on virtual realities or inward development. The motivations of extraterrestrial civilizations could also be guided by ethical considerations far different from our own, governed by principles and values we have yet to comprehend. If we ever encounter such civilizations, it will compel us to confront our assumptions about intelligence, morality, and the ultimate goals of life. Understanding their nature and motivations would not only answer fundamental questions about our place in the universe, but also challenge us to examine and potentially redefine our own objectives and values. Communicating with extraterrestrial intelligence, should we ever find it, presents a fascinating array of challenges and opportunities that span linguistics, mathematics, technology, and even psychology. Given the likely vast differences in biology, sensory perception, and cognitive processes, establishing a common ground for communication might initially seem daunting. However, scientists believe that certain universal principles, such as mathematics and physics, could serve as foundational elements for a mutual understanding. One of the most promising methods involves using radio waves, as they can traverse the vast distances of space relatively undistorted. Initiatives like the Search for Extraterrestrial Intelligence, SETI, have long targeted specific frequencies, particularly the hydrogen line, at 1,420 MHz, which is naturally occurring and might be universally recognized. If we do receive such a signal, the first step would involve confirming its extraterrestrial origin and then deciphering any potential patterns or information it carries. To send our own messages, scientists have crafted attempts at universal communication, such as the Arecibo message, transmitted in 1974, which encoded basic numerical data, atomic numbers of essential elements, DNA structures, and simple representations of human beings and the solar system. Visual methods might also be employed, using optical signals such as laser pulses to encode information. Another approach could be the transmission of digital data packets encoded with fundamental concepts, starting small and expanding in complexity. Successful historical attempts, like the Pioneer plaques and the Voyager Golden Records, have included visual and auditory information about Earth and humanity's understanding of the universe. These artifacts are designed to convey our presence, location, and cultural expressions, should they ever be discovered by an extraterrestrial civilization. In establishing a dialogue, we might employ artificial intelligence, AI, as intermediaries, creating software capable of learning and interpreting alien communication modes. By analyzing any received signals for patterns, repetitions, or other forms of structure, AI could help us identify the building blocks of their language. This would enable a back-and-forth exchange, evolving iteratively as both civilizations strive for clearer mutual understanding. Ultimately, the first steps in communicating with extraterrestrials will likely rely on our shared existence within the same universe, leveraging universal constants in math and science to build a bridge of understanding. While the process might be slow and arduous, the potential rewards of such communication, in terms of knowledge, cultural exchange, and a deeper understanding of life in the cosmos, are beyond measure. The possible forms and structures of alien life are as diverse as the environments they might inhabit, bounded only by the laws of physics and chemistry. Given the variety of planetary conditions in the universe, alien life could exhibit remarkable adaptations that support survival in extreme conditions. Some theorists suggest considering Earth's extremophiles, life forms thriving in environments once thought uninhabitable, as a starting point for imagining extraterrestrial biology. For instance, thermophiles thriving in boiling hot springs or acidophiles surviving in extremely acidic conditions demonstrate life's potential for flexibility. On rocky planets similar to Earth, alien life might possess familiar features like cellular structures, but with variations adapted to local conditions. For instance, on a planet with higher gravity, creatures might evolve shorter, sturdier forms to support their weight, or, conversely, in lower gravity environments, life forms might be larger and more elongated. If a planet has a thicker atmosphere rich in carbon dioxide but lacking in oxygen, you might find photosynthetic organisms with pigmentation adapted to the specific wavelengths of light penetrating their atmosphere. Aquatic worlds could give rise to life forms with advanced navigation systems, bioluminescence for communication, and propulsion mechanisms optimized for fluid dynamics. On icy moons like Europa or Enceladus, which are believed to harbor subsurface oceans, life could resemble Earth's deep-sea organisms found near hydrothermal vents. These alien life forms might rely on chemosynthesis rather than photosynthesis, deriving energy from chemical reactions involving substances like hydrogen sulfide or methane. These organisms could range from simple microbes to more complex multicellular entities clustered around fissures in the ice where nutrient-rich water emerges. Consider also worlds with radically different chemical compositions, such as Titan, Saturn's largest moon, which has lakes of liquid methane and ethane. Here, potential life could be based on entirely different biochemistry, utilizing methane as a solvent rather than water. Such life forms would need cellular machinery capable of operating at incredibly cold temperatures, perhaps using cell membranes made of substances appropriate for a methane environment like nitrogen-based compounds. Theoretical life forms in gas giant atmospheres like Jupiter could resemble massive, floating, balloon-like entities with gas sacs for buoyancy and mechanisms to harvest energy from atmospheric lightning or chemical gradients. These organisms might have elaborate systems for navigating winds, avoiding predatory floaters, or capturing smaller organisms. In imagining extraterrestrial life, it's crucial to maintain an open mind. The diversity of planetary environments means that life could evolve in ways that challenge our Earth-centric perspectives. Each discovery of extreme conditions on Earth where life thrives broadens our understanding of the possible forms that life can take, fueling the search for life's myriad manifestations across the cosmos. Techno-signatures are indicators that suggest the presence of advanced technological activities by an extraterrestrial civilization, and they offer promising clues in the ongoing search for intelligent life. Alien megastructures, such as Dyson spheres, are among the most intriguing forms of techno-signatures. A Dyson sphere is a hypothetical construct proposed by physicist Freeman Dyson, where a civilization encircles its star with an array of solar collectors or habitats to harness a substantial portion of the star's energy output. Detecting such a structure could indicate an advanced civilization that has reached a high Kardashev scale, specifically Type 2, capable of utilizing the full energy potential of its star. Scientists search for these megastructures by observing anomalies in stellar light patterns. For instance, a star diminishing in brightness over time, in a manner inconsistent with natural phenomena like planets or asteroid belts, might suggest the presence of an artificial megastructure. The most famous candidate for such a hypothetical observation is the enigmatic star K-ICE 8462852, commonly known as Tabby's star. Its irregular and significant dips in brightness have sparked discussions about the possibility of a Dyson sphere, although natural explanations like comet swarms are also considered. In addition to megastructures, other techno-signatures might include artificial light from cities on exoplanets, which could be detected as unusual optical signatures on the planet's night side. Industrial pollution in a planet's atmosphere is another telltale sign. For example, certain industrial pollutants, such as chlorofluorocarbons, CFCs, do not occur naturally and would indicate advanced technological activity. Spacecraft propulsion could also be a clue, as advanced civilizations might use powerful propulsion mechanisms whose energy emissions could be detectable across great distances. Radio signals, particularly those that are narrowband and structured, are traditional techno-signatures that SETI initiatives focus on. These signals can be differentiated from natural sources if they exhibit constant frequencies or modulated patterns indicating intelligence. Breakthrough. LISTEN, a comprehensive SETI program, utilizes this approach by scanning the skies for unusual radio emissions from distant star systems. Maser beams, emissions of microwave radio waves structured in a focused beam, are another possibility. If an alien civilization uses laser or maser communication technologies, intercepting these could provide direct evidence of intelligent life. Optical SETI searches for brief, intense bursts of light, which might be a form of high-speed, high-energy communications used by distant civilizations. While the search for techno-signatures is complex and fraught with the challenge of distinguishing artificial signals from natural phenomena, the discovery of such signs would be revolutionary. It would provide concrete evidence of technologically advanced civilizations beyond Earth, fundamentally altering our understanding of our place in the cosmos and opening new avenues for communication and exchange with our cosmic neighbors. Discovering a new fundamental force of nature through space observations would be a transformative event in the realm of physics, cosmology, and our overall understanding of the universe. Currently, we recognize 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The discovery of a 5th force would not only challenge these established frameworks, but also open new avenues for scientific exploration and technological innovation. From a cosmological perspective, a new force could help explain phenomena that don't quite fit within the existing models. For instance, the mysterious nature of dark matter and dark energy, which together make up about 95% of the universe, remains one of the most perplexing issues in modern astrophysics. A newly identified force might offer insights into these enigmatic components, perhaps revealing how they interact with visible matter, or suggesting why our universe is expanding at an accelerating rate. Such a discovery could unify disparate observations, providing a more cohesive understanding of cosmic evolution and structure. The implications would extend deeply into fundamental physics, potentially prompting a revision of the Standard Model, the theoretical framework that describes the relationships between subatomic particles and forces. A 5th force could necessitate the inclusion of new fundamental particles, lead to the reinterpretation of previously known particles, or even inspire a wholly new paradigm for understanding matter and energy. This could stimulate groundbreaking experiments both in particle physics laboratories on Earth and in space-based observatories. On a practical level, the discovery might have far-reaching technological ramifications. Historically, advances in our understanding of fundamental forces have led to significant technological leaps. Mastery of electromagnetism paved the way for modern electric power, telecommunications, and computing. Insights into the strong and weak nuclear forces have driven innovations in energy production and medical imaging. A new fundamental force could similarly catalyze novel technologies, potentially revolutionizing energy generation, propulsion systems, and materials science, perhaps even paving the way for new methods of space travel or resource utilization. Moreover, this groundbreaking discovery could influence other scientific disciplines, from chemistry to biology, by shedding light on previously unexplained phenomena at various scales. If life or other processes are influenced by this new force, it could have implications for our understanding of biology, potentially leading to medical advancements or novel biomaterials. Superseding intellectual advancements, the profound philosophical impact of discovering a new fundamental force would echo through cultures worldwide. It would underscore the limits of human knowledge and the beauty of scientific inquiry, inspiring future generations of scientists, engineers, and thinkers to question, explore, and innovate. Such a discovery serves as a potent reminder of our ever-evolving understanding of the universe, reinforcing the key scientific principle that reality is far richer and more intricate than our current models suggest. A Type 3 civilization, as defined by the Kardashev scale, would possess the capability to harness the energy output of an entire galaxy. This is a staggering notion, as it implies manipulating and utilizing energy sources on the scale of hundreds of billions of stars, along with other celestial bodies like black holes, neutron stars, and interstellar gas clouds. The impact of such a civilization on the universe would be profound and multifaceted, reshaping our understanding of advanced technological capabilities and the potential for interstellar interactions. One of the most significant ways a Type 3 civilization could affect the universe is through large-scale engineering projects, such as the construction of Dyson spheres around numerous stars. A Dyson sphere is a hypothetical megastructure composed of a swarm of satellites orbiting a star to capture its energy. Scaling this concept up to an entire galaxy means the civilization would be capable of manipulating stellar energy on an unprecedented scale, potentially even altering the life cycle of stars to optimize energy production. Such activities could result in observable changes in the luminosity and structure of the galaxy, which might be detectable by astronomers on Earth. Moreover, such a civilization would likely possess advanced methods of space travel and communication, potentially including warp drives, wormholes, or other forms of faster-than-light travel. This would enable interstellar colonization and resource extraction on a galactic scale, significantly impacting the distribution and utilization of matter and energy. These technologies could also allow for extensive terraforming projects, turning otherwise inhospitable planets into habitable worlds, thus expanding the reach of life in the galaxy. The environmental impact of these activities could be immense. A Type 3 civilization could influence galactic climate, magnetic fields, and radiation levels. They might even engage in large-scale astroengineering projects, such as redirecting asteroid belts, controlling star formation in nebulae, or harnessing black holes for energy. This could dramatically alter the natural evolution of the galaxy, leaving a distinct, detectable signature of their presence. The civilization's knowledge and technological prowess would be so advanced that they might engage in activities incomprehensible to us, such as manipulating dark matter or dark energy. By understanding and potentially controlling these mysterious components of the universe, they could further influence cosmic scales and dynamics. The discovery of such a civilization would not only answer the profound question of whether advanced extraterrestrial life exists, but also redefine our place in the universe. It could offer unparalleled opportunities for knowledge exchange and technological transfer, potentially catapulting human civilization to higher levels of development. The philosophical and cultural implications would be equally profound, triggering a re-evaluation of our aspirations, ethics, and the fundamental nature of intelligence and progress. Finally, a Type 3 civilization could potentially play a role in the long-term survival of life in the cosmos. They might develop strategies to mitigate existential threats, such as stellar collisions, supernova, and even the eventual heat death of the universe. Their advanced understanding of physics and engineering could provide solutions to challenges that are currently beyond our reach, ensuring the continuity of life and intelligence over astronomical timescales. The implications of humanity becoming an interstellar species are profound, encompassing scientific, cultural, ethical, and existential dimensions. Venturing beyond our solar system to settle other star systems would represent a monumental leap in human capability and ambition, fundamentally altering nearly every aspect of our civilization. Scientifically, the transition to an interstellar species necessitates breakthroughs in propulsion technology, life support systems, and sustainable habitats. Mastering faster-than-light travel, or developing advanced cryogenic sleep or generation ships capable of long-duration journeys would be prerequisites. Such advancements would lead to significant progress in fields like physics, engineering, biotechnology, and artificial intelligence. The search for potentially habitable exoplanets would also intensify, necessitating enhanced astronomical technologies and methods of remote sensing to identify suitable worlds and understand their environments. Now, culturally, becoming interstellar would mean the spread of human cultures across multiple planets, leading to unprecedented diversity in social structures, languages, traditions, and ways of life. The isolation of interstellar distances would likely mean that these new human societies evolve independently, reflecting the founders' values and adapting to their specific planetary conditions. This diversification could yield valuable new perspectives and solutions to common challenges, but also requires careful consideration of governance, identity, and unity across vast distances. Ethically, the potential to influence or disrupt extraterrestrial ecosystems raises significant questions. As we explore and colonize new worlds, we must develop frameworks for responsibly interacting with alien environments, avoiding contamination, and potentially coexisting with indigenous life forms if they are discovered. Ethical principles would need to address issues of environmental stewardship, respect for potential extraterrestrial intelligence, and equitable access to interstellar resources. Economically, the resources required for interstellar colonization would be immense, initially demanding coordinated international collaboration and investment. However, successful colonization could eventually yield new sources of minerals, energy, and other materials, reshaping economies and industries. Space could become the next frontier for economic development, driving innovations in resource extraction, transportation, and manufacturing. On an existential level, becoming an interstellar species offers a form of long-term survival insurance for humanity. It mitigates the risk of planetary catastrophes, such as asteroid impacts, climate change, or self-inflicted disasters like nuclear war, which could threaten life on Earth. Diversifying the locations of human civilization helps ensure that our legacy endures by spreading the risk across multiple worlds. Furthermore, the psychological and philosophical impacts of interstellar travel and colonization would be profound. Encountering entirely new planetary systems and, potentially, extraterrestrial life may lead to a deeper understanding of our place in the universe. It might stimulate a renewed sense of curiosity, purpose, and unity within humanity as we collectively engage in one of the grandest endeavors imaginable. Ultimately, becoming an interstellar species represents the next step in humanity's evolution, embodying our innate curiosity and drive to explore the unknown. It would redefine our capabilities and horizons, influencing every facet of human life and potentially marking the beginning of a new era in our cosmic journey. The prospect of manipulating spacetime for faster-than-light (FTL) travel, while currently in the realm of theoretical physics, presents exciting possibilities that could transform humanity into an interstellar species. Achieving this feat would require overcoming significant scientific and engineering challenges, but several theoretical frameworks provide a glimpse into how future technologies might make it possible. One of the most well-known concepts for FTL travel is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. The idea involves creating a warp bubble that contracts spacetime in front of a spacecraft and expands it behind, effectively allowing the craft to traverse vast distances faster than the speed of light without locally breaking the speed limit set by Einstein's theory of relativity. Inside the bubble, the spacecraft remains stationary relative to its immediate surroundings, allowing it to bypass the relativistic constraints. To create such a warp bubble, the technology would need to manipulate spacetime on a massive scale, potentially requiring exotic forms of matter or energy with negative energy density, often referred to as exotic matter. While this remains purely hypothetical, advances in quantum field theory, particularly around phenomena like the Casimir effect, suggest that negative energy might not be beyond reach. Significant progress in understanding and harnessing quantum mechanics and general relativity would be paramount. Another theoretical framework is the concept of wormholes, shortcut tunnels through spacetime connecting distant regions. Predicted by solutions to Einstein's field equations, wormholes could theoretically allow instantaneous travel between vastly separated points in space if they could be stabilized and made traversable. Ensuring the stability of a wormhole might again involve exotic matter to prevent it from collapsing. The challenge lies in creating or finding natural wormholes and then devising methods to control them. Technologies enabling the manipulation of spacetime might also draw from advances in quantum computing and quantum entanglement. Quantum computers could potentially solve complex equations governing spacetime dynamics, optimizing the conditions needed for warp drives or wormhole stabilization. Meanwhile, utilizing quantum entanglement might offer novel communication methods across vast distances, sidestepping the limits imposed by light speed. Further possibilities involve leveraging extremely powerful electromagnetic fields or gravitational waves. Advanced forms of propulsion might emerge from novel understandings of these phenomena, suggesting means to distort spacetime or generate the energy densities necessary for FTL travel. Concepts like Krasnikov tubes, a proposed network of paths through spacetime allowing FTL travel by altering spacetime geometry, might also come to fruition as our technology and theoretical understanding advance. The realization of such technologies would demand not only breakthroughs in physics and engineering, but also unprecedented levels of energy manipulation and control. It is conceivable that future advancements in harnessing the fundamental forces of nature, perhaps tapping into dark energy or devising entirely new forms of energy production, could provide the power required for these space-time manipulations. While FTL travel is theoretical and speculative at present, the scientific pursuit of these ideas drives innovation and expands our understanding of the universe. As history has shown, many breakthroughs that seemed impossible or purely theoretical eventually became reality through persistent inquiry and technological advancement. The dream of faster-than-light travel continues to inspire scientists and visionaries, pushing the boundaries of what humanity might someday achieve in our quest to explore the cosmos. Imagine for a moment stumbling upon a message from a civilization that existed millions of years before our own, originating from a distant part of the cosmos. The implications of such a discovery are nothing short of monumental. This revelation would fundamentally alter our understanding of our place in the universe. It would serve as a stark reminder that intelligent life has the potential to rise, flourish, and possibly fade away on cosmic scales of time. The content of the message itself could be a treasure trove of scientific and cultural knowledge, offering insights into technologies and advances far beyond our current capabilities. It could include their observations of the universe, maybe even historical accounts of their achievements and struggles, painting a picture of a vibrant, thriving society that once gazed at the stars, much like we do. Simultaneously, this discovery would spark countless debates and ethical considerations. What could have caused their extinction? Could their fate hint at potential existential risks for humanity, prompting us to reassess our priorities and vulnerabilities? On an existential level, learning about an extinct civilization would reinforce the fragility of life and the unique opportunity we have to forge our path in the cosmos. Researchers would eagerly mine the message for clues, hoping to understand the causes behind their demise, environmental, technological, or otherwise. Ultimately, it would be a humbling experience, uniting humanity with a profound sense of shared identity and shared destiny, as we collectively seek to ensure that our legacy does not end up as some distant echo in the cosmic timeline.